1. Why is Mercury shrinking and getting smaller every year? Imagine an entire planet wrinkling like an apple forgotten at the bottom of the food bowl. Not over millions of years, but now, at this very moment, as you breathe. Mercury, the smallest planet in the solar system and the closest to the Sun, is literally shrinking in size. Its surface is covered with enormous cliffs, some up to 3 kilometers high, that stretch for hundreds of kilometers like deep scars on the skin of a sleeping giant. These formations, called lobate scarps, are not geological accidents. They are wounds opened by a relentless process. The planet is shrinking as its interior cools, and the rigid crust is forced to break and fold upon itself, like the skin of fruit drying in the sun. What makes this truly extraordinary is not just that Mercury is shrinking, it's that this shrinkage may still be happening today, in real time, on a planet that was born more than 4 billion years ago. It's like discovering that a mummified corpse still has a beating heart inside, weak but persistent, refusing to stop completely. And the evidence for this is carved into the planet's surface, in fractures so recent they haven't yet been erased by time and the incessant bombardment of meteorites that have been hammering Mercury for billions of years. The discovery of this phenomenon was made possible by the MESSENGER probe, an acronym for Mercury Surface, Space Environment, Geochemistry, and Ranging, which orbited Mercury between March 2011 and April 2015, before disintegrating against its surface in a planned impact. During the final 18 months of the mission, when the spacecraft's altitude was drastically reduced to just a few kilometers above the surface, the cameras revealed something scientists didn't expect to find. Small, fresh fractures, so sharp and well-defined that they could only have formed recently. These fractures, known geologically as graben, are narrow depressions surrounded by parallel faults, about 150 meters deep and a few kilometers long. They appear on top of the giant scarps themselves, a kind of scar upon scar, a fracture within another fracture. What shocked the researchers was the youth of these structures. Mercury is constantly bombarded by meteorites and micrometeorites, a process called impact gardening that gradually buries and smooths any surface feature. Rocks are pulverized into dust, craters are filled with debris, sharp edges are rounded by the accumulation of material ejected from distant impacts. This process is relentless and predictable. If the fractures were more than 300 million years old, they would have already been masked, their edges softened, their contours erased by dust accumulated over eons. But they are there, perfectly visible, with edges as sharp as if they had been cut yesterday. And 300 million years, in geological terms, is yesterday. It's more recent than the dinosaurs. It's so recent that when these fractures opened on Mercury's surface, on Earth, the first reptiles were beginning to dominate the continents, and the ancestors of mammals were still small and insignificant creatures hiding in the shadows. The scientific team at the Open University, led by researchers who spent years analyzing every pixel of MESSENGER's high-resolution images, mapped 727 of these fractures, scattered across the entire planet. Of that total, 190 were classified as certain, due to the unequivocal clarity of their morphology. Flat depressions bordered by parallel scarps, sometimes interspersed with horsts, elevated blocks that share a scarp with an adjacent carbon. These small scars are distributed across 13 of Mercury's 15 mapping quadrangles, from 72 degrees north latitude to 76 degrees south. They appear on scarps of all sizes, from small wrinkle ridges to immense cliffs that cut across the surface for hundreds of kilometers. 97% of the certain carbon are located on lobate scarps, Mercury's most dramatic compression structures. This global distribution is crucial. This is not a local anomaly, not a specific region that happens to still be active. It's a planetary response. The entire planet is still contracting, and the entire crust is still responding to that contraction with new fractures. There is a particularly dense concentration of carbon around the Caloris Basin, a gigantic impact scar 1,550 kilometers in diameter, one of the largest records of violence in the solar system. The crust in this region may be thinner, which makes the lithosphere more prone to flexing and subsidence. This means that the impact that created Caloris, an event that occurred billions of years ago when the solar system was still young and violent, is still influencing Mercury's geology today, affecting how and where the crust deforms as the planet shrinks. Mercury's scars are not just records of the past. They are living structures, evolving, responding to forces that still shape the planet. 2. The liquid iron at Mercury's heart. At the center of Mercury pulses a heart of metal. Not a beating heart, but a gigantic core of liquid iron, so vast it occupies almost 3/4 of the planet's diameter. To put this in perspective, if you could cut Mercury in half like an orange, you would see a thin layer of rock, a mantle only 600 kilometers thick, surrounding a colossal sphere of molten iron, a ball of metal larger than the entire moon. This core is not pure iron. Under the extremely reducing conditions in which Mercury formed, significant amounts of silicon dissolved into the iron, creating an iron-silicon alloy that fundamentally alters the planet's thermal and magnetic behavior. This unique composition makes Mercury a natural laboratory for understanding how light elements behave under the crushing pressures and scalding temperatures of planetary interiors. The core is not motionless. Even now, convection currents flow through the liquid iron, generating a weak but measurable magnetic field, about 1% the intensity of Earth's magnetic field, but still present, still active. This magnetosphere, first detected by the Mariner 10 probe in the 1970s and confirmed by MESSENGER, is evidence that despite billions of years of cooling, Mercury's heart still beats with enough energy to twist and shape the space around it. It is a planet that refuses to die completely, that still carries within it a remnant of the primordial fire that created it. But why does Mercury have such a disproportionate core? Why is 70% of this planet's mass metal, while Earth, much larger, has only 32%? This is one of the great unanswered questions of planetary science, and the theories attempting to explain it are as violent as they are fascinating. One proposal suggests that in the chaotic early days of the solar system, Mercury was hit by a catastrophic impact that stripped away much of its rocky mantle, leaving behind only a thin shell over a massive core. This scenario is called the giant impact hypothesis, and there is evidence supporting it. Mercury's density is much higher than it should be for such a small planet, suggesting it lost something, probably mantle material rich in light silicates, which was ejected into space and never returned. Another proposal is that intense solar radiation, so close to the Sun, vaporized the lighter elements from Mercury's primitive mantle over millions of years, concentrating the heavy metals at the center. This is the vaporization hypothesis, and it's plausible because Mercury orbits in a region where surface temperatures can reach 430 degrees Celsius during the day, hot enough to melt lead. A third theory suggests that Mercury formed from a cloud of dust and gas that was already metal-rich from the start, perhaps because the young and violent solar winds of the primitive Sun blew light materials away from the inner region of the solar system, leaving only grains of iron and nickel to aggregate and form planets. Whatever the origin, the result is a world dominated by metal, a planet whose very identity is tied to the iron it carries within. And that iron is cooling. Thermodynamic models show that as the core's temperature decreases, iron begins to crystallize at the boundary between the liquid outer core and the solid inner core. This solidification process releases latent heat, energy stored in the phase change, that drives convection and sustains the magnetic field. But it's an asymmetric and complex process. Depending on the concentration of silicon in the alloy, the core can crystallize from the bottom up, from the top down, or even form separate liquid layers at different depths. Each scenario implies a different thermal history, a different path of planetary evolution. Recent laboratory experiments, conducted under conditions that replicate Mercury's core, pressures up to 40 gigapascals and temperatures of 2,500 degrees Celsius, revealed something surprising. In certain iron-silicon compositions, iron can undergo a phase transition from a body-centered cubic crystal structure to a face-centered cubic structure as it cools. This transition requires a small degree of supercooling, about 10 to 40 Kelvin, and can occur progressively over geological time. If this is happening in Mercury's core, it means the planet is undergoing an internal structural transformation that releases additional heat, prolonging its geological activity far beyond what would be expected for such a small and ancient world. It's possible that Mercury is not just slowly dying. It may be living a second act, a thermal resurrection fueled by the very phase changes of the iron at its heart. Studies suggest the core cools at a rate of approximately 30 Kelvin per billion years, a glacial process in human terms, but geologically active. And there is evidence that this cooling is slowed by thermal insulation mechanisms, a layer of liquid iron sulfide surrounding the inner core, a thick megaregolith on the surface, and the cessation or inefficiency of mantle convection. All these factors conspire to keep heat trapped, to prolong the planet's thermal agony, to ensure that Mercury continues shrinking for billions of years to come. 3. Scars billions of years old. Mercury's surface is an archive of violence. Every crater, every scarp, every fracture tells a story of impact, compression, and deep time. But among all these marks, the most revealing are the Graben, narrow depressions bordered by parallel faults, carved into rock like grooves left by giant fingers. These structures are not large. Many are only a few tens of meters deep and a few kilometers long, but their importance is enormous. Graben form when the crust is locally stretched, creating stresses that open fissures in the rock. On Mercury, paradoxically, they appear atop compression structures, the lobate scarps and wrinkle ridges that form when the crust is pushed upward by tectonic forces. It's as if, after raising a mountain, the mountain itself begins to crack at the summit, victim of the internal stresses that created it. This combination of global compression and local extension creates a complex and fascinating pattern of deformation, unique in the solar system. Imagine Mercury's crust as a sheet of paper you crumple into a ball. As you squeeze, the sheet folds and wrinkles into ridges. But at the top of each ridge, where the material is most stretched, small tears begin to appear. This is what's happening on Mercury, but on a planetary scale and with immensely greater forces. And the most fascinating thing is that these fractures are not ancient relics. They are fresh. They are young. They may be forming right now. What makes Mercury's Graben extraordinary is not just their existence, but their youth. When the Messenger mission entered its final low-orbit phase, a risky and deliberate phase that allowed the spacecraft to plunge to altitudes as low as a few kilometers above the surface before finally crashing into the planet, the high-resolution cameras revealed that many of these Graben have sharp and well-defined edges, without the signs of degradation you would expect from ancient structures. On a world constantly bombarded by meteorites and micrometeorites, any surface feature is gradually buried and smoothed. Rocks are pulverized into dust, craters are filled with debris. Sharp edges are rounded by the accumulation of material ejected from distant impacts. This process is relentless and predictable, and it can be quantified. Studies of lunar boulder tracks, marks left by boulders that rolled downhill on the Moon and were photographed by the Apollo missions, allowed scientists to estimate the rate of filling for shallow depressions, approximately 5 centimeters per million years on the Moon. But Mercury has a thicker regolith than the Moon, due to a higher regolith production rate, and also has a higher micrometeorite flux, which means that the abrasion of surface features by micrometeorite impactors is greater. Topographic diffusivity measurements show that craters on Mercury degrade at least twice as fast as same-sized craters on the Moon. Therefore, applying a conservative filling rate of 10.7 centimeters per million years, double the lunar rate, scientists calculated that the visible carbon on Mercury must have formed less than 300 million years ago. Otherwise, their morphological signatures would have already been masked, buried under layers of dust accumulated over eons. But the Open University team went further. They measured the shadows cast by the Graben in high-resolution images, an established and precise method used for decades in planetary geology, to determine their depths. They traced construction lines along the shadow-casting edge, drew measurement lines in the direction opposite to the solar azimuth, and applied corrections for the spacecraft's position relative to the Sun. They made 331 depth measurements for 99 of the certain carbon on 29 of the 48 shortening structures. 220 measurements yielded depths less than 50 meters. 92 were between 50 and 100 meters. Only 19 were greater than 100 meters. These are shallow depressions, but still visible, still defined. Then, they compared the length of each carbon to its measured depth and plotted the data on a displacement versus length graph, a graph that compares Mercury's fractures with populations of normal faults on Earth and the Moon. The result was revealing. Most of the data clustered within the expected range for terrestrial and lunar faults, but plotted slightly below the terrestrial data, consistent with theoretical predictions that faults on Mercury should have smaller displacements for a given length due to different gravity. This suggests that the Graben follow the same physical laws that govern fractures on Earth and the Moon, but that they have been only slightly filled. If they were very old, the data would plot much lower in the displacement length field, indicating Graben that are shallow relative to their inferred length. But that's not what the data show. They show Graben that are still close to their original depths, Graben that haven't had enough time to be significantly buried. And using standard displacement length scaling relationships and estimated filling rates, the team calculated ages for each Graben. Many were formed in the last 200 to 300 million years, some possibly in the last 100 million years, and some maybe even younger. So young that their ages are indistinguishable from zero within the margins of error. This means that Mercury's tectonics is not a dead phenomenon, confined to the first billions of years of its history. It's an active, ongoing process that may be happening at this very moment. And when the Bepi-Colombo mission, a collaboration between the European Space Agency and the Japan Aerospace Exploration Agency, arrives at Mercury and begins its observations, we will have the opportunity to see these fractures with unprecedented resolution, perhaps even detect new Graben that have formed since. Messenger's last visit. Imagine that, witnessing in real time the contraction of an entire world. Imagine being able to compare images separated by a decade and see with your own eyes a new scar that wasn't there before. That is the power of planetary exploration. That is the privilege of living in an era when we can observe other worlds not as static points of light, but as dynamic planets, alive, changing, before our eyes. 4. The paradox of the planet closest to the Sun. There is something profoundly counterintuitive about Mercury's fate. Here is a world that orbits closer to the Sun than any other planet, a scorched sphere that experiences the full fury of our star's radiation, where surface temperatures soar to 430 degrees Celsius during the day, hot enough to melt lead, hot enough to make tin puddle and flow like water. And yet, despite all this heat, despite being bathed in solar energy more intense than anywhere else in the solar system, Mercury is cooling. Its massive iron core is losing heat, contracting, pulling the planet's crust inward like a deflating balloon. How can this be? How can a planet so close to an inferno be freezing to death? The answer lies in one of the most fundamental principles of physics, and in understanding it, we glimpse the strange and lonely nature of planetary existence in the vacuum of space. Heat, in our everyday experience, moves through contact. A hot stove heats a pot. A warm hand warms a cold one. This is conduction, the transfer of thermal energy through direct physical contact between materials. But in space, there is nothing to touch. Between Mercury and the Sun lies 150 million kilometers of vacuum, and between Mercury and everything else lies even more emptiness. There is no air to carry heat away, no water to conduct it, no material medium through which thermal energy can flow. And so Mercury cannot cool the way objects cool on Earth. It can only cool through radiation, the emission of electromagnetic waves, primarily in the infrared spectrum, that carry energy away from the planet's surface and into the void. Radiation is a slow and inefficient way to lose heat, especially for a small world like Mercury. The rate at which an object radiates energy is governed by the Stefan-Boltzmann law, which states that the power radiated per unit area is proportional to the fourth power of the object's absolute temperature. This means that hotter objects radiate much more efficiently than cooler ones. A body at 1,000 Kelvin radiates 16 times more energy per square meter than a body at 500 Kelvin. But it also means that as an object cools, its rate of cooling decreases dramatically. The cooler Mercury becomes, the slower it cools. And unlike Earth, which has active plate tectonics that constantly recycle crustal material and transport heat from the interior to the surface, Mercury has a thick, stagnant lid, a rigid outer shell that acts as an insulator, trapping heat inside. The planet's mega-regolith, a layer of pulverized rock created by billions of years of meteorite bombardment, further insulates the interior. Studies suggest this layer could be several kilometers thick, and regolith is an excellent thermal insulator because it's full of tiny air pockets. Except on Mercury, of course, there is no air. But there are vacuum pockets, which are even better insulators. Heat trying to escape from Mercury's core must diffuse slowly through 600 kilometers of solid rock mantle, then through kilometers of fractured, pulverized regolith, before it can finally radiate away from the surface. This is a journey that takes geological ages. And so, Mercury cools, but agonizingly slowly, losing its primordial heat degree by painful degree over billions of years. But there is another layer to this paradox, another reason why Mercury's cooling is so slow and so strange. During the day, Mercury's surface absorbs enormous amounts of solar radiation, about 10 times more energy per square meter than Earth receives. But at night, when the sun disappears below the horizon, the surface cools rapidly, radiating that absorbed heat back into space. The temperature swings on Mercury are the most extreme in the solar system. from 430 degrees Celsius at noon to minus 180 degrees Celsius before dawn, a range of 610 degrees. No other world experiences such violent thermal variations. But here's the critical point. These temperature swings affect only the very surface, the topmost few centimeters of regolith. Heat does not penetrate deeply into the ground because regolith is such a poor conductor, and heat from the interior does not easily escape to the surface for the same reason. The result is a thermal decoupling between Mercury's surface and its interior. The surface responds almost entirely to solar heating, cycling wildly between day and night, while the interior cools at its own pace, indifferent to the chaos above. Missions to Mercury have used infrared spectrometers to measure the thermal inertia of the surface, essentially how quickly the surface temperature responds to changes in solar heating, and found values consistent with a thick layer of loose, powdery regolith overlying solid rock. This regolith blanket is simultaneously heated by the sun and insulated from the interior, creating a strange thermal environment where the surface and the deep interior exist in separate thermal regimes, barely communicating with each other. And so, Mercury continues its slow march toward thermal death, its core cooling at a rate of about 30 Kelvin per billion years, its surface enduring the most extreme temperature variations in the solar system, and somehow, against all intuition, these two realities coexist on the same small world, separated by mere kilometers but isolated by the physics of heat transfer in a vacuum. 5. Venus, the planet that spins backward. If you could stand on the cloud tops of Venus and watch the stars wheel overhead, assuming you could survive the crushing atmospheric pressure and the sulfuric acid rain, you would notice something deeply wrong with the sky. The stars would rise in the west and set in the east, exactly opposite to what happens on Earth, on Mars, on Jupiter, on almost every other world in the solar system. Venus rotates backward, or more precisely, it rotates retrograde, clockwise when viewed from above the north pole of the solar system, while almost everything else rotates counterclockwise. This is not a subtle anomaly, not a slight orbital peculiarity. This is a fundamental reversal of planetary motion, and it demands an explanation. Planets form from rotating disks of gas and dust surrounding young stars, and those disks have angular momentum. They spin in a particular direction, and that spin is inherited by everything that forms within them. By rights, every planet, every moon, every asteroid should spin in the same direction as the original protoplanetary disk, and most do. But Venus does not. It turns the wrong way, slowly and stubbornly, taking 243 Earth days to complete a single rotation. And because its orbit around the Sun takes only 225 Earth days, a Venusian day, one complete cycle of daylight and darkness, actually lasts longer than a Venusian year. Time itself moves strangely on Venus, measured in rhythms that defy our terrestrial intuitions. The most widely accepted explanation for Venus's retrograde rotation is catastrophic collision. In the violent early history of the solar system, when planets were still accreting from the debris of the protoplanetary disk and gravitational interactions flung objects into chaotic orbits, collisions were common. Earth itself was struck by a Mars-sized impactor in an event that created the Moon, melted the entire surface of our planet, and fundamentally reshaped its composition and structure. Venus, orbiting in the same inner region of the solar system, would have experienced similar bombardment. Computer simulations show that if Venus were struck by a large impactor, perhaps 10 to 20% of Venus's mass, at the right angle and velocity, the impact could reverse the planet's rotation entirely. The energy involved would be staggering, enough to melt the entire crust and possibly vaporize the oceans that some models suggest Venus once possessed. The planet would have been reshaped by violence, its spin torqued backward by the physics of a bleak collision. But there's a problem with this theory. Such a massive impact should have left other traces. A large moon formed from the ejected debris, perhaps, or a compositional anomaly in the crust. Venus has no moon. And while our knowledge of Venus's interior composition is limited, we've only ever landed a handful of probes on its surface, and none survived more than a few hours in the hellish conditions. There's no obvious evidence of the kind of large-scale differentiation you might expect from a giant impact. So the collision hypothesis, while plausible, remains unproven. An alternative explanation involves tidal interactions with the Sun and atmospheric effects. Venus has an incredibly dense atmosphere, 92 times the pressure of Earth's atmosphere at sea level, composed mostly of carbon dioxide, with thick clouds of sulfuric acid. This atmosphere moves. It super-rotates, meaning the upper atmosphere circles the planet much faster than the planet itself rotates, completing a full circuit in just 4 Earth days. The winds at cloud level reach speeds of 100 meters per second, hurricane-force winds that race around the planet in a phenomenon that remains poorly understood. These atmospheric motions exert torque on the planet's surface through friction and pressure gradients. Over hundreds of millions of years, this atmospheric drag could, in theory, slow down and even reverse a planet's rotation. Add to this the gravitational pull of the Sun, which creates tidal bulges in Venus's solid body and in its massive atmosphere, and you have a complex system of forces acting over geological time. Recent modeling suggests that Venus's current retrograde rotation could be an equilibrium state, a balance between solar tides trying to lock the planet with one face always toward the Sun, and atmospheric torques acting in the opposite direction. In this scenario, Venus didn't necessarily flip overnight. It may have simply slowed its original prograde rotation, passed through a period of no rotation at all, and then began rotating backward, settling into the strange state we observe today. But this too is speculative. The truth is, we don't know for certain why Venus spins backward. We have theories, we have models, we have possibilities. But the planet itself remains enigmatic, wrapped in its sulfuric clouds, guarding its secrets, turning slowly against the cosmic grain. 6. The infernal pressure and the lead rain. To understand Venus is to understand pressure. Not the pressure of deadlines or obligations, but physical pressure, the weight of atmosphere, the crushing force of gas piled kilometers deep above your head. On Earth, at sea level, the atmosphere exerts a pressure of about 100 kilopascals, or 1 bar, which is simply the weight of all the air molecules stacked above you, stretching up to the edge of space. On Venus, the pressure at the surface is 9.2 megapascals, or 92 bars. This is not an abstract number. This is the pressure you would experience if you dove 90 meters underwater on Earth, the pressure at the depth where recreational scuba diving ends and technical diving begins, where nitrogen narcosis clouds your mind and your lungs are compressed to a fraction of their normal volume. Except on Venus, this is the pressure at the surface, before you descend into any valleys or lowlands. And unlike water, which you can at least see through, Venus's atmosphere is opaque, a thick orange haze that scatters light and reduces visibility to perhaps a few dozen meters. Soviet Venera landers, the only spacecraft to successfully transmit images from Venus's surface, showed a dim, rocky landscape bathed in a strange orange glow, like the perpetual twilight of a world that never sees direct sunlight. The sky is not black, not blue, but a diffuse, sourceless luminescence filtering down through 90 kilometers of carbon dioxide and sulfuric acid clouds. It is a landscape of pressure and heat and toxic chemistry, fundamentally hostile to anything we would recognize as life. But the pressure is only the beginning. The temperature at Venus's surface is 467 degrees Celsius, hot enough to melt lead, hot enough to make zinc flow like honey. This is hotter than Mercury, despite Venus being twice as far from the Sun. The reason is the runaway greenhouse effect. Carbon dioxide, which makes up 96% of Venus's atmosphere, is a greenhouse gas. It allows visible light from the Sun to pass through and heat the surface, but it absorbs the infrared radiation that the surface tries to radiate back into space. The heat is trapped. And with an atmosphere 92 times denser than Earth's, the greenhouse effect on Venus is catastrophic. Every photon of infrared radiation trying to escape is absorbed and re-emitted, thousands of times before it finally reaches space. The result is a planet where the surface temperature barely varies between day and night, between equator and poles, because the atmosphere is so thick and so efficient at redistributing heat that local variations are erased. Venus is uniformly hellish, everywhere, always. And in this environment, strange chemistry occurs. Lead, with a melting point of 327 degrees Celsius, would exist as a liquid on Venus's surface. Zinc, with a melting point of 420 degrees, would be at the edge of melting. Some researchers have speculated about metallic frost or metal snow on the mountains of Venus, highlands where the temperature drops just enough for heavy metals vaporized from the lowlands to condense and precipitate out of the atmosphere. This is not just speculation. Radar observations from the Magellan spacecraft, which orbited Venus from 1990 to 1994 and mapped the planet's surface with unprecedented detail, showed that the highlands of Venus, regions like Maxwell Montes, the highest mountain on the planet, towering 11 kilometers above the mean planetary radius, have unusual radar reflectivity. The surfaces are brighter in radar than the lowlands, suggesting they are coated with something metallic. The leading hypothesis is tellurium-based compounds, or possibly pyrite, iron sulfide, which can exist in the hot, high-pressure environment of Venus's lowlands, but would decompose or react at lower pressures. As you ascend into the highlands, the temperature drops slightly, perhaps 20 or 30 degrees, and the pressure decreases. This creates a frost line where certain metal compounds can condense. It's not snow as we know it. It's not water ice falling gently from the sky. It's heavy metal compounds precipitating out of a carbon dioxide atmosphere in a world where the air is thick as water and the ground glows red with heat. And this is what Venus offers us: a laboratory of extreme chemistry, a place where the familiar rules are pushed to their breaking point and new phenomena emerge. When we send new missions to Venus, and there are several planned for the next decade, including NASA's Veritas and Da Vinci missions and ESA's Envision, we will have the chance to study this alien chemistry in detail, to understand how atmospheres can trap heat so efficiently that they transform a planet into a furnace, and perhaps to learn lessons about the fate of atmospheres on worlds beyond our solar system, on the thousands of exoplanets we are now discovering around other stars. 7. Mars and its global dust storms. Mars is a world of dust. Not the gentle household dust that accumulates on shelves, but a fine, talcum-like powder of oxidized iron minerals. Rust, essentially, ground down over billions of years by the relentless freeze-thaw cycles, the ultraviolet radiation, and the thin atmosphere that once was thick enough to support liquid water on the surface. This dust is everywhere on Mars. It coats the rocks, fills the craters, drifts into dunes that march slowly across the plains, like frozen waves, and occasionally, perhaps once or twice per decade, this dust rises. It begins locally, perhaps in the southern hemisphere during late spring, when the sun heats the surface and creates powerful convection currents. Small dust devils, miniature tornadoes of swirling dust, form and dissipate, thousands of them dancing across the landscape. But sometimes, under the right conditions, these local storms grow. They merge, feeding on the temperature difference between the dusty air and the clearer air around them. The dust absorbs sunlight, heating the atmosphere, creating more convection, lifting more dust. It's a positive feedback loop, a runaway process that can engulf an entire hemisphere in a matter of weeks. And then, in the worst cases, the storm goes global. The entire planet disappears beneath a veil of suspended dust, and Mars transforms from a world of subtle surface details into a featureless orange sphere, blotting out mountains, canyons, polar caps, everything obscured beneath the churning haze. The 2018 global dust storm was one of the most dramatic in recent memory. It began in late May as a localized storm in the Arabia Terra region. But within days, it had spread, and by mid-June, it had encircled the entire planet. Observations from NASA's Mars Reconnaissance Orbiter showed the atmospheric opacity, measured in tau, where higher values indicate more dust, skyrocket to values above 10. At such opacities, the amount of sunlight reaching the surface drops to less than 1% of normal. The sky, normally a butterscotch haze during daytime, turned dark as twilight. Solar-powered rovers on the surface suddenly found themselves in deep trouble. The Mars Exploration Rover Opportunity, which had been operating far beyond its planned 90-day mission, it had been exploring Mars for 14 years, sent its final transmission on June 10, 2018. The message, poetically interpreted by engineers, essentially said, "My battery is low and it's getting dark." And then, silence. The dust storm had blocked so much sunlight that Opportunity's solar panels could not generate enough power to keep its systems running. The rover entered a deep sleep mode, designed to preserve critical systems until sunlight returned. Mission controllers waited. The storm eventually cleared by September, as it had to. Dust storms on Mars are self-limiting because once enough dust is suspended in the atmosphere, it begins to cool the place.
Surface, reducing convection and allowing the dust to settle. But Opportunity never woke up. Perhaps a critical component failed during the months of cold and darkness. Perhaps its internal clock drifted too far, preventing it from knowing when to try to recharge. Perhaps dust accumulated on its solar panels, coating them so thickly that even when the skies cleared, not enough light could penetrate. We will never know for certain. Opportunity is still there, somewhere in Perseverance Valley, a silent monument to exploration, covered in a thin layer of Martian dust. But why does Mars have such extreme dust storms when no other planet does? The answer lies in Mars's unique combination of atmospheric and surface conditions. Mars's atmosphere is thin, only about 6 millibars of pressure at the surface, less than 1% of Earth's atmospheric pressure, but it's thick enough to move dust. The terminal velocity of a dust particle in Mars's thin atmosphere is high, meaning particles fall slowly, so once dust is lofted into the air, it can stay suspended for weeks or months. Mars's gravity is only 38% of Earth's, which also helps keep dust aloft longer. And crucially, Mars has no oceans, no large bodies of water to moderate temperature swings or to trap dust. The entire surface is dry, exposed, available to be picked up and carried by the wind. Earth has dust storms too. The Sahara Desert generates massive dust plumes that cross the Atlantic Ocean, but they are regional, confined by geography and weather patterns. Earth's thicker atmosphere and stronger gravity also mean that dust settles quickly. On Mars, the combination of low gravity, thin atmosphere, and a completely desiccated surface creates the perfect conditions for planet-wide dust mobilization. And there's a seasonal component. Mars's orbit is significantly elliptical, much more so than Earth's, which means the intensity of sunlight varies considerably over the course of a Martian year. When Mars is closest to the Sun, which happens during southern summer, the southern hemisphere receives intense solar heating. This is also when the southern polar cap, composed of carbon dioxide ice, sublimates rapidly, releasing gas into the atmosphere and increasing atmospheric pressure and wind speeds. These strong winds can initiate dust storms, and once a storm starts during this season, it has the maximum amount of solar energy available to drive the feedback loop that leads to global expansion. Scientists have been studying Martian dust storms for decades, using both orbiting spacecraft and surface rovers, trying to understand the conditions that trigger a regional storm to become global. It's not fully predictable. Some Martian years pass with only small, local storms. Others produce planet-encircling events. And understanding this process is not just academic curiosity, it's essential for future human missions. Astronauts on Mars will need to know when dust storms are coming, how long they will last, and how to protect their equipment and habitats from the infiltrating dust that finds its way into every seal, every joint, every mechanism. 8. The mystery of Mars's lost water. Look at Mars through a telescope and you see a dry, cold desert, a planet of rust-red plains, dark volcanic rocks, and polar caps of frozen carbon dioxide and water ice. It seems lifeless, barren, a world where water, if it exists at all, is locked away as ice beneath the surface or hidden in tiny pockets of brine too salty to freeze. But this was not always Mars. If you could travel back in time 4 billion years, you would find a very different world. The sky might have been blue. Rivers might have flowed through valleys, feeding into lakes, and perhaps even an ocean that covered much of the northern lowlands. Rain might have fallen. Clouds might have drifted across a thicker atmosphere. This ancient Mars, warm, wet, potentially habitable, is not speculation. It is written in the rocks. Orbital imaging has revealed thousands of valley networks carved into the ancient highlands, branching and merging in patterns that can only be explained by flowing water. There are outflow channels, enormous trenches hundreds of kilometers long and several kilometers wide, carved by catastrophic floods that would have dwarfed anything in Earth's history. There are sedimentary rocks, layered deposits laid down in standing water, containing minerals like clays and sulfates that form only in the presence of liquid water. And there are deltas, fan-shaped deposits where rivers once emptied into lakes, now preserved in exquisite detail by the dry Martian climate. Jezero Crater, where NASA's Perseverance rover is currently exploring, contains one such delta, a frozen moment in geological time showing that 3.5 billion years ago, this crater was filled with water, and a river flowed into it from the west, depositing sediments in layers that are now being drilled and analyzed for signs of ancient microbial life. But the water is gone. Mars today contains only a tiny fraction of the water it once held. The polar caps contain perhaps enough water ice to cover the planet to a depth of 10 to 20 meters if melted and spread evenly, and there are subsurface ice deposits at mid-latitudes detected by ground-penetrating radar. But this is nothing compared to the volume of water required to carve the valleys and fill the lakes and sustain the rivers that clearly existed in Mars's past. So where did it all go? This is one of the central mysteries of Mars, and solving it requires understanding the entire history of the planet's atmosphere, climate, and geology. Part of the water is still there, locked beneath the surface. Radar data from Mars Express and the Mars Reconnaissance Orbiter
have revealed what may be subsurface lakes of liquid water, kept from freezing by dissolved salts and geothermal heat. Drilling would be required to confirm these findings, but the evidence is suggestive. However, subsurface reservoirs cannot account for all the missing water. Most of it was lost to space. Mars lost its atmosphere, and when the atmosphere went, the water went with it. The mechanism is well understood. Mars is small, only about half the diameter of Earth and 1/10 the mass. Its lower gravity means it has a weaker hold on its atmosphere. And crucially, Mars lost its global magnetic field early in its history, perhaps 3.8 to 4 billion years ago, when the planet's core cooled enough that the dynamo generating the field shut down. Without a magnetic field to shield it from the solar wind, the stream of charged particles constantly flowing from the Sun, Mars's atmosphere was exposed and vulnerable. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, was specifically designed to study atmospheric loss. Its instruments measure the composition and dynamics of the upper atmosphere, tracking how atoms and molecules are stripped away by the solar wind. The results have been striking. MAVEN has shown that Mars loses about 100 grams of atmosphere to space every second, a rate that seems small, but over billions of years, it adds up to the loss of an entire thick atmosphere. The process works like this. Solar ultraviolet radiation ionizes atoms in the upper atmosphere, giving them an electric charge. The solar wind, which carries a magnetic field with it, interacts with these charged particles and accelerates them, flinging them into space. During solar storms, when the Sun ejects bursts of particularly intense radiation and charged particles, the atmospheric loss rate increases dramatically. MAVEN observed this directly during a solar storm in March 2015, when the stripping rate increased by a factor of 10. Over geological time, this process has been relentless. The early Sun was more active, with more frequent and more powerful solar storms, which means atmospheric loss was even faster in Mars's youth. And as the atmosphere thinned, the surface pressure dropped. Water can exist as a liquid only within a narrow range of temperature and pressure. As the pressure dropped below about 6 millibars, the triple point of water, liquid water became unstable. It would either freeze or evaporate, and any vapor would be broken apart by ultraviolet radiation into hydrogen and oxygen, with the light hydrogen escaping to space. This is the slow death of Mars, a planet that began with an atmosphere thick enough to sustain a hydrological cycle that gradually lost its protective magnetic field, that watched its atmosphere bleed into space molecule by molecule, and that saw its rivers and lakes evaporate and freeze, leaving behind only the ghosts of water in dry riverbeds and the salts deposited when ancient seas evaporated. And yet, the story may not be over. Water ice exists beneath the surface. Seasonal flows, recurring slope lineae, appear on crater walls during warm seasons, suggesting that liquid brines may occasionally seep from the subsurface. And the search for life continues. If life arose on Mars when water flowed, it may have retreated underground when the surface dried, persisting in aquifers kilometers below, waiting to be discovered. 9. The invisible auroras of Jupiter. Jupiter has auroras, but you will never see them with your eyes. Stand on the cloud tops of Jupiter, if such a thing were possible, if there were anything solid to stand on rather than the endless kilometers of hydrogen and helium gas compressed by gravity into gradations of increasing density until eventually the gas becomes so squeezed that it behaves more like liquid metal than air. And look up toward the poles. You would see nothing unusual. The sky would glow with the reflected light of the sun, and perhaps you would see lightning in the distance, flickering between cloud layers.
But the auroras, the most powerful and energetic auroras in the entire solar system, would be invisible to you. They shine not in visible light, but in ultraviolet and X-rays, wavelengths that human eyes cannot detect, wavelengths that require specialized instruments to observe. And what instruments reveal is extraordinary. Jupiter's auroras are permanent features, glowing ovals centered on the magnetic poles, fed by a continuous stream of charged particles accelerating along magnetic field lines at velocities approaching the speed of light. Unlike Earth's auroras, which flicker and dance and respond to the variable solar wind, Jupiter's auroras are powered primarily by the planet itself, by the interaction of Jupiter's enormous magnetic field with the volcanic moon Io, which spews out tons of sulfur and oxygen ions every second, creating a torus of plasma that encircles Jupiter and feeds the auroral engine. Jupiter's magnetic field is a monster. It is 20,000 times stronger than Earth's magnetic field at the surface, and it extends millions of kilometers into space, creating a magnetosphere so vast that if you could see it from Earth, it would appear several times larger than the full moon in the sky. The Sun's own magnetic field, carried by the solar wind, crashes against this magnetosphere and is deflected, creating a bow shock where the supersonic solar wind is suddenly slowed and heated. Inside the magnetosphere, Jupiter's field dominates, and unlike Earth, where the magnetic field is generated by the motion of liquid iron in the outer core, Jupiter's field is generated by the motion of liquid metallic hydrogen in the deep interior. Hydrogen compressed to such extreme pressures that the electrons are stripped from their atoms, and the hydrogen conducts electricity like a metal. This bizarre state of matter exists nowhere else in the solar system in such quantities, and it creates a dynamo far more powerful than anything on Earth. The field lines loop from pole to pole, and charged particles follow these lines, spiraling along them as they are accelerated to tremendous energies. When these particles, mostly electrons and ions, strike the upper atmosphere, they collide with hydrogen and helium atoms, exciting them and causing them to emit light. In the ultraviolet, Jupiter's auroras shine with the brightness of 1,000,000,000 watts, a continuous beacon of electromagnetic radiation screaming out into space. But it's not just the Sun and Io that power these auroras. Jupiter itself rotates rapidly, once every 10 hours, and this rotation drags the magnetic field around with it. The magnetosphere does not rotate as a rigid body, but instead stretches and distorts, and the plasma trapped within is flung outward by centrifugal force, creating a current system that flows along magnetic field lines from the equatorial regions down to the poles. This is called the magnetosphere-ionosphere coupling current, and it adds another layer of complexity to the auroral system. The result is that Jupiter's auroras have multiple components. A main oval corresponding to the boundary of open and closed field lines, bright spots corresponding to magnetic footprints of the Galilean moons. Each moon carves out its own path through Jupiter's magnetic field, creating a wake of disturbed plasma that maps down to the auroral zone, and transient features that brighten and fade over minutes to hours. The Hubble Space Telescope has been observing Jupiter's auroras for decades, building up a library of images that reveal the dynamic, ever-changing nature of these phenomena. The Juno spacecraft, which has been orbiting Jupiter since 2016, carries instruments that measure the particles and fields directly, flying through the auroral zones and measuring the electron beams that create the light. Juno has discovered that the electrons responsible for Jupiter's X-ray auroras are accelerated by a process called wave-particle interaction, where electromagnetic waves in the magnetosphere resonate with the electrons and boost them to energies of several mega-electron volts, relativistic speeds, where the electrons are moving at a significant fraction of the speed of light. These are not gentle phenomena. These are some of the most energetic particle acceleration processes in the solar system, occurring continuously, pouring energy into Jupiter's upper atmosphere at a rate that exceeds the total energy output of human civilization by orders of magnitude. And yet, from Earth, with the naked eye, Jupiter appears as a serene, bright star, a calm, steady light in the night sky, betraying nothing of the violence occurring at its poles.
10. The perfect hexagon of Saturn. Saturn has a secret at its north pole, and that secret is geometry. Not the soft, flowing curves of clouds shaped by wind and weather, not the chaotic turbulence of storms that form and dissipate according to the whims of atmospheric dynamics, but a shape so precise, so regular, so utterly unexpected that when it was first discovered by the Voyager spacecraft in the 1980s, some scientists wondered if it could be an artifact of image processing, a glitch in the data. But it was real. Centered on Saturn's north pole is a hexagon, a six-sided jet stream with each side measuring approximately 14,500 kilometers, making it wider than the diameter of Earth. The sides are remarkably straight, the corners sharp, and the entire structure rotates with the planet once every 10 hours and 39 minutes, which is the rotation period of Saturn's deep interior as measured by radio emissions. This hexagon is not painted on the surface. Saturn has no surface, only layers of gas and liquid hydrogen extending down thousands of kilometers until pressure and temperature become so extreme that matter enters exotic states we can barely replicate in laboratories. The hexagon is a wave pattern in the atmosphere, a standing wave locked into place by some combination of wind speeds, Coriolis forces, and the geometry of the planet itself. And it has persisted for decades. The same hexagon photographed by Voyager in 1980 and 1981 was still there when Cassini arrived in 2004, unchanged in its basic structure, though the colors and cloud features within it had shifted and evolved. Why a hexagon? Why not a pentagon or an octagon, or simply a circular vortex like the polar features on other planets? This question has driven atmospheric scientists to construct experiments and simulations trying to replicate the phenomenon. In 2010, researchers at Oxford University created a laboratory analog using a cylindrical tank filled with fluid, rotated at different speeds at the center and the edge to create shear, a difference in velocity that mimics the jet streams on Saturn. They found that under certain conditions, the shear flow spontaneously organized into polygonal shapes, triangles, squares, hexagons, depending on the rotation rate and the fluid properties. The number of sides is determined by the wavelength of instabilities in the flow, perturbations that grow and interact, eventually locking into a stable pattern. On Saturn, the hexagon corresponds to a specific balance between the eastward jet stream at approximately 77 degrees north latitude and the rotation of the planet beneath it. The jet stream acts as a barrier, a river of wind flowing at speeds of about 320 kilometers per hour, and within this river, waves propagate and interfere with each other. The hexagon is what mathematicians call a non-linear standing wave, a self-sustaining pattern that emerges from the equations of fluid dynamics when the parameters fall into a narrow range. Change the wind speed slightly, or the thickness of the atmospheric layer, or the temperature gradient, and the pattern would shift to a different polygon or dissolve into chaos. Saturn, by chance or by some deeper principle we don't yet understand, sits precisely at the parameters that produce a hexagon. But the hexagon is not alone at Saturn's pole. Nested within it, at the exact center, is a massive vortex, a hurricane-like storm with an eye 50 times larger than the average hurricane eye on Earth. This eye, approximately 2,000 kilometers across, is surrounded by towering clouds that rise above the surrounding atmosphere, and within the eye itself, the air is relatively clear and calm, just as in terrestrial hurricanes. But unlike hurricanes on Earth, which are powered by the release of latent heat from condensing water vapor and which drift across the planet's surface until they encounter land
or cooler water and dissipate, Saturn's polar vortex is locked in place, fed by the heat rising from Saturn's deep interior. Saturn radiates about twice as much energy as it receives from the Sun. Heat left over from its formation and from the gravitational compression of helium rain falling through the hydrogen atmosphere. This internal heat source means Saturn's weather is driven from below as much as from above, creating dynamics fundamentally different from Earth's solar-driven climate. The polar vortex has been observed continuously by Cassini throughout its 13-year mission, and it shows complex structure, multiple nested rings of clouds rotating at different speeds, spiral arms feeding into the center, and periodic brightening events where clouds suddenly appear in the eye and then dissipate. The Cassini mission ended in 2017, when the spacecraft, low on fuel, was deliberately plunged into Saturn's atmosphere to avoid any possibility of contaminating the potentially habitable moons Enceladus and Titan. But before it died, Cassini sent back unprecedented high-resolution images of the hexagon and the central vortex, revealing details down to a few kilometers in scale. Images that will keep atmospheric scientists busy for decades, extracting every piece of information about wind speeds, cloud altitudes, temperature structures, and the three-dimensional circulation patterns that maintain this bizarre geometric feature. And the hexagon remains, rotating silently at Saturn's pole, a testament to the hidden order that can emerge from chaos. A six-sided riddle written in clouds and wind, waiting for the next mission to Saturn to study it again, and perhaps, finally, to fully understand why nature chose this particular shape. 11. The seismic waves that revealed Mars's interior. For most of human history, we understood planetary interiors only by inference. We could measure a planet's mass, calculate its density, observe how it wobbled or responded to tidal forces, and from these external clues, we could build models of what might lie beneath the surface. But these were educated guesses, constrained by physics, but never confirmed by direct observation. On Earth, we had a unique advantage: seismology. Earthquakes generate waves that travel through the planet's interior, and by measuring how these waves propagate, how fast they travel, how they bend and reflect at boundaries between different materials, seismologists constructed a detailed picture of Earth's internal structure. We know the thickness of the crust, the depth of the mantle, the size of the outer and inner core, and even the composition and temperature of each layer, all from analyzing the vibrations of earthquakes recorded by seismographs scattered across the globe. But could we do the same for Mars? Could we place a seismograph on another planet and listen to its heartbeat? For decades, the answer was no, or at least not successfully. The Viking landers in the 1970s carried seismometers, but they were mounted on the landers rather than directly on the ground, and every gust of wind shaking the spacecraft created noise that overwhelmed any genuine seismic signals. But in November 2018, NASA's InSight lander touched down on Mars carrying the most sensitive seismometer ever deployed on another planet, designed specifically to detect the faint vibrations of Marsquakes and to finally peer inside the red planet. InSight, interior exploration using seismic investigations, geodesy, and heat transport, was a stationary lander, meaning it did not roam across the surface like a rover, but instead stayed in one place, focusing all its energy on geophysical measurements. Its seismometer, called SEIS, the Seismic Experiment for Interior Structure, was designed and built by a consortium of European institutions, led by France's space agency, CNES, and it was extraordinarily sensitive. Sensitive enough to detect ground motion smaller than the width of a hydrogen atom.
sensitive enough to hear Marsquakes so faint that if they occurred on Earth, they would be completely lost in the background noise of human activity, ocean waves, and atmospheric turbulence. But Mars is seismically quieter than Earth. It has no plate tectonics, no massive earthquakes, no subduction zones where slabs of crust grind against each other, generating magnitude 9 events. Mars's seismic activity is subtle, the result of the planet slowly cooling and contracting, stresses accumulating in the crust, and occasionally releasing in small fractures. The question was, would there be enough Marsquakes of sufficient magnitude to allow InSight to construct a seismic profile of the interior? The answer, over the course of InSight's 4-year mission, was
a resounding yes.
SEIS detected over 1,300 Marsquakes, ranging from tiny tremors barely distinguishable from noise to several events above magnitude 4, large enough to be felt if you were standing on the surface, and large enough that their seismic waves traveled deep into the planet and returned, carrying information about the structure they passed through. The results were revelatory. By analyzing the arrival times and waveforms of seismic waves from hundreds of Marsquakes, the InSight science team, a global collaboration of seismologists, geophysicists, and planetary scientists, constructed the first direct measurements of Mars's interior structure. They found that Mars's crust is thinner than expected, perhaps only 20 to 30 kilometers thick in the lowlands and 50 to 70 kilometers in the highlands, compared to Earth's continental crust, which averages about 40 kilometers. This thin crust suggests that Mars differentiated early in its history, with heavy metals sinking to the core and leaving behind a relatively thin, rocky shell. The mantle extends from the base of the crust down to about 1,500 kilometers depth, and it appears to be relatively cold and rigid, confirming that Mars lacks the vigorous convection currents that drive plate tectonics on Earth. But the biggest surprise came from the core. Seismic waves that pass through the planet's center, called PKP waves, using the nomenclature of terrestrial seismology, travel at speeds that indicate Mars's core is liquid, not solid. And more surprisingly, the core is larger than expected, approximately 1,800 to 1,900 kilometers in radius, which means it extends halfway to the surface. This is a huge core for a planet of Mars's size, accounting for about half the planet's diameter. And a liquid core of that size implies something about Mars's thermal history. The core has not cooled enough to begin crystallizing, which means either Mars is retaining heat more efficiently than models predicted, or the core contains light elements, perhaps sulfur, oxygen, or hydrogen dissolved in the iron, that lower the melting point and keep the metal liquid. Later in the mission, InSight detected seismic waves from meteorite impacts on the far side of Mars, and the way these waves reflected off the core allowed scientists to refine their models further, even detecting hints of a transition zone at the base of the mantle that might represent a change in mineral structure. And then, in December 2022, after 4 years of operation, InSight's power finally failed, as dust accumulated on its solar panels, and the lander fell silent. But the data it returned will be analyzed for years, each seismic waveform a fossil of Mars's interior, a recording of vibrations that traveled through rock and metal to tell us what lies beneath.
12. The mystery of Jupiter's accelerating rotation. Jupiter spins fast, faster than any other planet in the solar system. Despite being the most massive planet, with more than twice the mass of all other planets combined, Jupiter completes a full rotation in just under 10 hours. This rapid spin creates a powerful Coriolis effect that organizes Jupiter's clouds into the distinctive bands we see through telescopes.
dark belts and bright zones, with narrow jet streams at the boundaries flowing at speeds exceeding 400 kilometers per hour. For centuries, astronomers assumed that these clouds, located in the upper atmosphere at pressures of about 1 bar, were merely the visible surface of a planet-wide circulation pattern, and that the deeper atmosphere below rotated more or less uniformly with the same 10-hour period. After all, Jupiter is made almost entirely of hydrogen and helium, gases that become denser with depth but remain fluid. There is no solid surface to anchor flows, no continents to disrupt circulation. It seemed reasonable to assume that the atmosphere would rotate as a coherent body, perhaps with some vertical shear, but nothing dramatic. But when NASA's Juno spacecraft arrived at Jupiter in 2016 and began its series of highly elliptical orbits, diving to within 5,000 kilometers of the cloud tops and then swinging out to millions of kilometers before plunging back in, it carried instruments that could measure Jupiter's gravitational field with extraordinary precision. And gravity, it turns out, can reveal rotation. How does gravity reveal rotation? The key is in the asymmetries. If Jupiter rotated as a perfectly uniform sphere with no internal motion, its gravitational field would be simple, strongest at the center, decreasing smoothly with distance, symmetrical. But Jupiter is not uniform. It bulges at the equator due to centrifugal force. The equatorial radius is about 7% larger than the polar radius, and this oblateness creates deviations in the gravity field called gravitational harmonics, labeled J2, J4, J6, and so on, representing progressively higher-order deviations from spherical symmetry. These harmonics were measured reasonably well before Juno arrived, but Juno measured them to much higher precision, and it also measured odd gravitational harmonics, J3, J5, J7, which should be 0 if Jupiter were symmetric north to south. The fact that these odd harmonics are not 0 means there is asymmetry between the northern and southern hemispheres, and the most likely explanation is that the atmosphere is not rotating uniformly. Different bands of clouds, different jet streams, are rotating at different speeds, and these differential rotations create mass asymmetries that Juno can detect as tiny perturbations in its orbit. By analyzing these gravitational anomalies and feeding them into sophisticated models of fluid dynamics on a rotating sphere, the Juno science team concluded that the jet streams visible at Jupiter's cloud tops penetrate deep into the planet, down to about 3,000 kilometers below the visible surface, or about 4% of Jupiter's radius. At that depth, the pressure and electrical conductivity become so high that the magnetic field exerts enough force to suppress differential rotation, and below 3,000 kilometers, the interior rotates as a rigid body. But above that depth, the atmosphere is dynamically active, with different latitudes rotating at different speeds, and this zone of differential rotation contains more mass than the entire Earth. But the real mystery emerged in 2021, when the Juno team published findings suggesting that not only do the jet streams penetrate deep, but the interior of Jupiter, the region below 3,000 kilometers, rotates faster than the outer atmosphere. This was unexpected. The expectation was that if there were any differential rotation, it would be the other way around. The surface would rotate faster due to angular momentum conservation as material moves toward the equator, while the deep interior would lag. But the data suggested the opposite. The deep interior, the metallic hydrogen region where Jupiter's powerful magnetic field is generated, appears to be spinning faster than the overlying layers, with rotation periods perhaps a few minutes shorter than the canonical 10-hour period measured from cloud tracking. This is difficult to explain. If the interior is rotating faster, what is driving it? One possibility is that the dynamo process itself, the motion of conducting fluid that generates the magnetic field, creates torques that spin up the interior. Another is that the process of helium rain, where droplets of liquid helium separate from the hydrogen and fall toward the center, carrying angular momentum with them, could be spinning up the core. Or perhaps the measurement is revealing not a true rotation difference, but a complex pattern of internal circulation, eddies, waves, or convective cells that create gravitational signatures mimicking differential rotation. The truth is, scientists are still debating what Juno's data really mean. The gravitational harmonics are measured with high precision, but translating those measurements into a picture of Jupiter's interior requires assumptions about the equation of state of hydrogen at extreme pressures, the depth of the magnetic field's influence, the efficiency of mixing, and a dozen other parameters that are poorly constrained. What is clear is that Jupiter's interior is not simple, not static, not a uniform ball of gas rotating serenely. It is dynamically complex, with layers and flows and processes that we are only beginning to glimpse. And when future missions return to Jupiter, perhaps with probes that descend deeper into the atmosphere, or orbiters with even more sensitive instruments, we will refine these measurements and perhaps finally understand what makes this giant planet spin the way it is.
Does. 13. Europa and the hidden ocean. Beneath the ice, beneath the cracked and frozen surface of Europa, lies an ocean. Not a metaphorical ocean, not a layer of damp soil or patches of underground ice, but a genuine liquid water ocean, perhaps 100 kilometers deep, containing more than twice the volume of all of Earth's oceans combined. This ocean has never seen sunlight. It has been sealed beneath a shell of ice, estimates range from 15 to 25 kilometers thick, for billions of years, isolated from the vacuum of space above and from direct contact with the rocky mantle below. And yet, this hidden sea may be one of the most promising places in the entire solar system to search for life beyond Earth. Europa is only slightly smaller than Earth's moon, and from a distance it appears as a bright, smooth sphere, the most reflective object in the solar system, its surface ice so pristine and white that it bounces back more than half the sunlight that strikes it. But look closer, and the surface reveals itself to be anything but pristine. It is covered with a network of dark lines, cracks, ridges, and bands that crisscross the surface in chaotic patterns, like a porcelain plate that has been shattered and reassembled. Some of these features are hundreds of kilometers long, and their darkness comes from minerals and salts brought up from below, staining the ice with the chemistry of the ocean beneath. The evidence for Europa's subsurface ocean comes from multiple lines of investigation built up over decades of observation. The first clues came from the Voyager spacecraft in 1979, which photographed Europa's strange surface and noted the absence of large impact craters. Strange for an object that has orbited in the gravitationally violent Jovian system for 4 billion years. The lack of craters suggested that the surface is young, perhaps only tens of millions of years old, constantly being resurfaced by some process that erases the scars of impacts. Then came the Galileo mission, which orbited Jupiter from 1995 to 2003 and made multiple close flybys of Europa. Galileo carried a magnetometer, an instrument that measures magnetic fields, and as it passed near Europa, the magnetometer detected something remarkable. Europa generates its own magnetic field, but not in the way planets like Earth do. Earth's field is generated by a dynamo in the liquid iron core. Europa's field, by contrast, is induced. It is created by the interaction of Jupiter's powerful magnetic field with a conductor inside Europa. Jupiter's magnetic field is so strong and rotates so rapidly that it sweeps past Europa. And if there is a layer of electrically conductive material within Europa, That layer will respond by generating currents, which in turn create a secondary magnetic field. The strength and orientation of the induced field that Galileo measured are consistent with a global layer of salty water. Salt dissolved in the water makes it conductive, beneath
ice shell. This was the smoking gun. Europa has an ocean. But how does liquid water survive so far from the sun, where surface temperatures hover around -160 degrees Celsius, cold enough to turn carbon dioxide into dry ice and oxygen into a liquid? The answer is tidal heating. Europa orbits Jupiter in a resonance with two other large moons, Io and Ganymede, such that for every orbit Ganymede completes, Europa completes 2 and Io completes 4. This resonance locks the moons into a gravitational dance that prevents their orbits from becoming perfectly circular. Instead, Europa's orbit is slightly elliptical, which means its distance from Jupiter varies over the course of each orbit. And because tidal forces depend on distance, they are stronger when Europa is closer to Jupiter and weaker when it is farther away, the shape of Europa is constantly changing, flexing and deforming as it orbits. The rocky interior rises and falls by about 30 meters with each tidal cycle, and the friction generated by this flexing heats the interior. It is the same process that makes Io the most volcanically active body in the solar system, but on Europa, the heating is gentler, just enough to keep the water beneath the ice from freezing. Calculations suggest that tidal heating deposits about 100 terawatts of power into Europa's interior, roughly comparable to the geothermal heat flux of Earth. This is not a lot of energy spread across an entire moon, but it is enough. Enough to maintain an ocean. Enough to drive convection in that ocean, circulating water between the ice shell and the rocky mantle below. Enough, perhaps, to power hydrothermal vents on the ocean floor, analogous to the vents on Earth's seafloor that support entire ecosystems of life independent of sunlight. Life that derives energy from chemical reactions between hot rock and seawater. And then, in 2012, the Hubble Space Telescope observed something extraordinary. Using its ultraviolet spectrograph, Hubble detected plumes of water vapor erupting from Europa's south polar region. Jets of material shooting 200 kilometers above the surface before falling back down. The observation was tentative, right at the limit of Hubble's sensitivity, but it was repeated in subsequent years, and though the plumes are not always visible, they seem to be intermittent, perhaps tied to Europa's position in its orbit when tidal stresses are highest. Their existence suggests that the ocean is not completely sealed. There are cracks, perhaps temporary fissures that open when the ice flexes, that allow water to escape from below. This is profound for two reasons. First, it means that a future mission to Europa would not need to drill through kilometers of ice to sample the ocean. It could simply fly through a plume and collect material directly, analyzing it for salts, organic molecules, and perhaps even microorganisms if they exist. Second, it means that the ocean is in contact with the surface, at least occasionally, which allows for exchange of materials and energy between the surface environment, which is constantly bombarded by radiation from Jupiter's magnetosphere, and the deep ocean, which is shielded and dark. This exchange could create chemical gradients, disequilibrium conditions that life could exploit. NASA is planning the Europa Clipper mission, scheduled to launch in 2024 and arrive at Jupiter in 2030, which will make dozens of flybys of Europa, mapping the surface, measuring the ice shell thickness with ice-penetrating radar, sampling any plumes it encounters, and searching for the best landing sites for a future mission that might one day touch down on this frozen moon and drill into the ice, seeking answers to one of humanity's oldest questions. Are we
alone. 14. The rings of Saturn are disappearing. Saturn's rings are dying. Not in the distant future, not as a theoretical prediction, but now, measurably, at a rate that can be quantified. Every second, approximately 10,000 kilograms of ring material, ice particles ranging in size from dust grains to boulders, are falling into Saturn's atmosphere, vaporizing in the heat of entry and becoming part of the planet. This process, whimsically called ring rain, was first detected by the Voyager missions in the 1980s, when instruments measured an unexpected influx of water molecules and charged particles at Saturn's equator. But it was NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017 and made history by diving between the planet and its rings during its final months, that measured the rain directly and calculated its rate. The findings were stark. At the current rate of loss, Saturn's rings will be gone, completely dissipated, in about 100 million years. This sounds like a long time, and it is by human standards, but in the 4.5 billion year history of the solar system, 100 million years is nothing. It is 2% of the age of the planets. It means that Saturn's rings are a temporary feature, a transient phenomenon, and we are living at a special moment in cosmic history when they happen to exist. Had humans evolved 100 million years in the future, Saturn would appear as a ringless gas giant, indistinguishable at a glance from Jupiter. Had we evolved 100 million years in the past, we might have seen rings even more magnificent than those that exist today. But where did the rings come from, and why are they disappearing? The origin of Saturn's rings has been debated for decades. One theory is that they are primordial, formed at the same time as Saturn itself from the debris of the protoplanetary disk that gave birth to the solar system. But this theory has problems. Ring particles are constantly colliding with each other, and each collision grinds them down, reducing larger particles to smaller ones, and eventually to dust. Computer simulations of ring dynamics suggest that even if the rings started out massive and bright, they would darken over time as meteoritic dust from interplanetary space coats the ice, and they would spread out and thin as particles exchange angular momentum. Yet Saturn's rings are bright, startlingly bright, composed of nearly pure water ice with very little contamination. This suggests they are young. Another theory is that the rings are the remains of a moon that ventured too close to Saturn and was torn apart by tidal forces. Every planet has a Roche limit, a distance inside which tidal forces, the difference in gravitational pull on the near side and far side of an object, exceed the object's self-gravity. If a moon crosses inside the Roche limit, it will be ripped apart, and the debris will spread out into a ring. This could explain why Saturn's rings are made of ice. The destroyed moon would have been an icy body, perhaps similar to Enceladus or Mimas. And it could explain the youth of the rings. If the destruction happened relatively recently, within the last few 100 million years, the rings would still be bright and clean, not yet darkened by eons of dust accumulation. Cassini's final plunge provided critical data to test these theories. As the spacecraft dove through the gap between Saturn and its innermost ring, it measured the mass of the rings by observing how their gravity perturbed Cassini's trajectory. The result? The rings contain about 40% of the mass of Mimas, Saturn's smallest major moon. This is surprisingly low. If the rings were primordial, you would expect them to be more massive, containing the leftover material from Saturn's formation zone. The low mass supports the idea that the rings are the remnants of a destroyed moon, and a relatively small one at that. Cassini also measured the rate of ring rain more precisely than ever before by analyzing data from its ion and neutral mass spectrometer, which detected water molecules and charged particles falling into Saturn's upper atmosphere along the planet's magnetic field lines.
The rings are not smooth, uniform disks. They have structure, gaps, and density waves sculpted by the gravitational influence of Saturn's many moons. And they are electrically charged by solar ultraviolet radiation and by impacts from micrometeoroids, which ionize some of the ice particles. These charged particles feel the pull of Saturn's magnetic field, and as they spiral along field lines, they are funneled into the planet's atmosphere at high latitudes, creating the ring rain. The rate of 10,000 kilograms per second sounds enormous, but spread across the entire ring system, which has a total mass of about 15,000 trillion kilograms, it implies a lifetime of about 100 million years. And there's another loss mechanism: meteoroid bombardment. High-speed impacts from interplanetary debris hit the rings constantly, and the most energetic impacts can eject ice particles with enough velocity to escape Saturn's gravity entirely, carrying ring material away into interplanetary space. When you add up all the loss mechanisms, ring rain, meteoroid erosion, and possibly interactions with Saturn's moons, the picture is clear. Saturn's rings are ephemeral, a beautiful accident of cosmic timing, and future generations, whether human or whatever intelligence might arise millions of years hence, will look at Saturn and see only a pale globe, ringless and diminished, with perhaps only the faintest halo of dust to hint at the glory that once was. 15. The Ice Volcanoes of Triton. Triton is a world of contradictions. It is one of the coldest places in the solar system, with surface temperatures of -235 degrees Celsius, cold enough that nitrogen, a gas in Earth's atmosphere, exists as ice on Triton's surface, forming polar caps and glaciers that flow sluggishly across the landscape. And yet, Triton is geologically active. It has geysers, not geysers of hot water like those in Yellowstone or Iceland, but cryovolcanic geysers, plumes of liquid nitrogen that erupt from beneath the surface, vaporize in the low pressure of Triton's thin atmosphere, and shoot upward for 8 kilometers before being caught by high-altitude winds and carried downwind for hundreds of kilometers, creating dark streaks across the ice where nitrogen snow and entrained dust settle back to the ground. These geysers were discovered by Voyager 2 in 1989, the only spacecraft ever to visit Neptune and its moons, and their existence was a complete surprise. Before Voyager, most scientists expected Triton to be a dead, frozen ice ball, geologically inert like most of the small moons in the outer solar system. But the images revealed a surface unlike anything seen before. Cantaloupe terrain, a region of strange polygonal depressions covering much of the northern hemisphere. Frozen lakes that had once been liquid and then refroze, trapping bubbles and leaving smooth, flat plains. And the geysers, called cryovolcanoes, actively venting material into space. Why is Triton active? The answer, as with Europa and Enceladus, is tidal heating. But Triton's situation is more complex and more tragic. Triton orbits Neptune backward, retrograde, meaning it moves in the opposite direction to Neptune's rotation. This is unique among large moons in the solar system. All major moons orbit in the same direction as their planet's rotation, because they formed from the same disk of material that formed the planet, and that disk had a net angular momentum that everything inherited. But Triton's retrograde orbit means it did not form where it is now. It was captured, likely from the Kuiper belt, that vast reservoir of icy bodies beyond Neptune. Capture is a rare and violent process. For Triton to be captured, it must have encountered Neptune at just the right velocity and angle, and there must have been a way to dissipate energy, perhaps a collision with another moon that once orbited Neptune, or a multi-body gravitational interaction that allowed Triton to shed velocity while something else was ejected. The details are lost to time, but the result is clear. Triton ended up in a retrograde, highly elliptical orbit around Neptune. and over hundreds of millions of years, tidal forces circularized that orbit, but at tremendous cost. The energy required to circularize an orbit does not disappear. It is converted to heat, deposited into the body being circularized. Triton's interior was melted by this process, heated by the friction of tidal flexing, until the moon was geologically reshaped, its original surface erased, its interior differentiated into a rocky core and an icy mantle. But the tidal heating did not stop when the orbit circularized. Triton's orbit is still slightly eccentric, and even a small eccentricity is enough to generate tidal flexing and internal heat. And crucially, Triton's retrograde orbit means it is slowly spiraling inward toward Neptune. Retrograde orbits are unstable in the long term because tidal forces acting on a retrograde moon break its orbital motion rather than boosting it, causing the moon to lose energy and fall closer to the planet. Calculations show that in about 3 to 4 billion years, Triton will cross within Neptune's Roche limit and be torn apart, its fragments spreading into a ring system that could rival or even exceed the magnificence of Saturn's current rings. But for now, Triton remains intact, and the tidal heating continues, maintaining pockets of liquid nitrogen beneath the surface. The geysers are driven by a seasonal mechanism. As Triton orbits Neptune, different parts of the surface are alternately illuminated and shadowed, because Neptune has seasons and Triton's orbit is inclined relative to Neptune's equator. When the sun finally shines on a region that has been in darkness for decades, the surface ice, translucent nitrogen ice, allows sunlight to penetrate several meters down, where it is absorbed by a darker sublayer, perhaps organic compounds or silicate dust. This subsurface heating warms the nitrogen ice just enough to turn it from solid to liquid, and the liquid nitrogen, under pressure from the overlying ice, finds cracks and weak points and erupts to the surface as a geyser. Voyager 2 observed at least 2 active geysers and several dark streaks indicating recent geyser activity. The plumes themselves are difficult to see because nitrogen gas is transparent, but the dark material entrained in the plumes, dust and organic compounds, creates visible columns and downwind deposits that can be mapped. And the atmosphere of Triton, though incredibly thin, surface pressure is only 14 microbars, about 70,000 times less than Earth's atmosphere, is sufficient to transport this material and distribute it across the surface, creating a complex cycle of eruption, transport, and deposition that continues to shape Triton's appearance. No spacecraft has returned to Triton since Voyager 2's fleeting encounter in 1989, but there are proposals for future missions, orbiters that would spend years studying Neptune and its moons, mapping Triton's surface in detail, measuring its atmosphere, and perhaps even witnessing new geyser eruptions as they happen. 16. Miranda, the Frankenstein moon. Miranda is small, only 470 kilometers across, barely large enough to be pulled into a sphere by its own gravity, and yet it is one of the most visually dramatic objects in the solar system. When Voyager 2 flew past Uranus in 1986 and turned its cameras toward this diminutive moon, scientists expected to see a bland, heavily cratered surface, much like the surfaces of Saturn's small moons or Jupiter's outer satellites. What they saw instead was chaos. Miranda's surface is a patchwork of wildly different terrains, as if the moon had been assembled from spare parts that didn't quite match. There are ancient, heavily cratered highlands, dark and rough, covered with impact scars that speak of billions of years of bombardment. And then, abruptly, these highlands give way to regions called coronae, bizarre, ovoid features with grooved and ridged surfaces, bright and relatively smooth, looking nothing like the terrain around them. 3 major coronae dominate Miranda's visible hemisphere.
Arden Corona, Elsinore Corona, and Inverness Corona, named after locations in Shakespeare's plays, following the convention of naming Uranian moons and their features after characters and places in the works of Shakespeare and Alexander Pope. These coronae are enormous relative to Miranda's size. Each is hundreds of kilometers across, covering a significant fraction of the moon's surface, and the boundaries between the coronae and the surrounding terrain are sharp, almost geometric, as if someone had cut out pieces of different worlds and stitched them together with visible seams. But the most striking feature of all is Verona Rupes, a cliff that runs along the edge of one of the coronae and plunges downward for at least 20 kilometers, possibly more, as the base of the cliff is in shadow in Voyager's images and the true depth remains uncertain. 20 kilometers. To put that in perspective, the Grand Canyon on Earth is about 1.8 kilometers deep at its deepest point. The cliff face of El Capitan in Yosemite, one of the most famous vertical rock faces on Earth, is less than 1 kilometer high. Verona Rupes is a cliff 12 times deeper than the Grand Canyon, a wall of ice and rock that drops so far that if you stood at the top and jumped, assuming you could survive in the vacuum and the minus 200-degree cold, you would fall for about 12 minutes before hitting the bottom. And due to Miranda's low gravity, only about 1% of Earth's, you would reach a maximum velocity of only about 200 kilometers per hour, far less than terminal velocity on Earth, and you might actually survive the impact if you landed in a deep drift of loose regolith. Not that anyone is planning to test this, but it's a thought experiment that captures the alien scale of this feature. Verona Rupes is not just a cliff. It is a boundary between worlds, a geological fault line that separates terrains of entirely different ages and compositions. What could create such a landscape? The leading theory is catastrophic disruption and reassembly. The idea is that Miranda was struck by a massive impactor early in its history, an impact so violent that it shattered the moon into pieces. But rather than dispersing into space, the fragments remained loosely bound by their mutual gravity and slowly reaccreted, falling back together over thousands or millions of years. The reassembly would not have been neat. Chunks of crust, mantle, and possibly core material would have come together in a haphazard arrangement, with heavy pieces sinking and light pieces floating. But the process would have been interrupted before complete differentiation could occur, frozen in place by the rapidly cooling ice. The result? A moon with a jumbled interior and a surface that shows pieces of its former selves stitched together. This theory explains the coronae as regions where partially differentiated material, perhaps warmer, more plastic ice from the interior, rose to the surface and flowed, creating the grooved and ridged textures seen today. It explains the sharp boundaries as the edges of reassembled fragments that never fully merged. And it explains the enormous cliffs as fault scarps created when different blocks of material settled at different rates, creating vertical displacements. But there are problems with this theory. For one, it's not clear that an impact could completely shatter a body of Miranda's size without ejecting the fragments entirely. The energy required to break apart the moon is enormous, and if you have that much energy, you likely have enough to overcome the moon's escape velocity and send the pieces flying. For another, if Miranda was reassembled, you would expect more evidence of heating and melting. Yet much of the surface appears cold and ancient. An alternative explanation is tidal heating. Miranda orbits Uranus in a system with 4 other major moons: Ariel, Umbriel, Titania, and Oberon. And in the past, these moons may have been locked in orbital resonances, similar to the Galilean moons of Jupiter. Resonances force orbits to be eccentric, and eccentric orbits create tidal heating. If Miranda experienced a period of intense tidal heating, perhaps hundreds of millions of years ago, its interior would have partially melted. Warmer, less dense ice would have risen in plumes toward the surface, breaking through the colder, rigid crust and creating the coronae as cryovolcanic features. The grooves and ridges would be extensional faults, created as the surface was pulled apart by rising diapirs of warm ice. And when the resonance eventually broke, perhaps due to tidal evolution of the orbits, the heating would have ceased, the interior would have refrozen, and Miranda would have been left with its bizarre patchwork surface, a snapshot of a brief period of geological activity in an otherwise dead moon. This theory avoids the need for catastrophic disruption and relies instead on processes we know occur on other moons. But it requires that Miranda was once in a resonance, and there is no direct evidence for this. Uranus's moons are not currently in resonance, and modeling their orbital evolution backward in time is difficult, because it depends on uncertain parameters like the moon's internal structures and tidal dissipation rates. So we are left with a mystery. Miranda's surface is undeniably strange, a frozen record of some dramatic event or process in its past. But we do not have enough data to say definitively what happened. Voyager 2's flyby was brief, just a few hours of close observation, and no spacecraft has returned to the Uranus system since. There are proposals for future missions, including a Uranus orbiter that would study the planet and its moons over multiple years, and Miranda is high on the list of targets. Imagine a spacecraft in orbit around Uranus, making repeated close flybys of Miranda, mapping every square kilometer with high-resolution cameras, measuring the gravity field to constrain the internal structure, using ice-penetrating radar to see beneath the surface. We could finally solve the mystery of the Frankenstein moon and learn what forces shaped this tiny, chaotic world. 17. The Silicate volcanism of Venus. Venus is not supposed to be volcanically active. It is roughly the same size as Earth, but it lacks plate tectonics, the process by which Earth's crust is constantly recycled, subducting at trenches and upwelling at mid-ocean ridges, a process that drives most terrestrial volcanism. Venus's crust appears to be a single, unbroken shell, a stagnant lid that does not move or recycle. And without plate tectonics, the conventional wisdom held, there should be no mechanism to bring fresh magma to the surface. Venus should be geologically dead, its surface frozen in time, shaped only by the slow erosion of wind and the occasional impact of a meteorite. But the evidence has been accumulating for years that Venus is not dead. Its surface, mapped in stunning detail by NASA's Magellan spacecraft in the early 1990s using synthetic aperture radar, shows hundreds of volcanoes, some small, some enormous, rivaling the largest on Earth. Mat Mons, the tallest volcano on Venus, rises 8 kilometers above the surrounding plains, comparable to Mauna Loa in Hawaii when measured from its base on the ocean floor. And around these volcanoes are lava flows, channels carved by rivers of molten rock, and vast plains covered with solidified lava that must have been liquid when it was emplaced. The question has always been, when did this volcanism occur? Is it ancient, a relic of a more active past, or is it recent, perhaps even ongoing? In 2023, scientists analyzing archival data from the Magellan mission announced a discovery that suggests Venus is volcanically active now. They used a technique called change detection, comparing radar images of the same region taken at different times during Magellan's mission, looking for features that appeared, disappeared, or changed in brightness. This is difficult with radar data because the brightness of a surface in radar depends on many factors: roughness, slope, composition, viewing angle,
and small differences in the spacecraft's position or orientation can create apparent changes that are not real. But one change stood out as undeniable. In the Atla Regio region, a volcanic highland near Venus's equator, a feature identified as a volcanic vent changed shape and size between two radar images taken 8 months apart. In the first image, the vent was a small, roughly circular depression about 2 square kilometers in area, surrounded by relatively smooth terrain. In the second image, the vent was larger, about 4 square kilometers, and the surrounding terrain showed new, rough textures consistent with fresh lava flows. The most plausible explanation is that the vent erupted during those 8 months, ejecting lava that filled part of the vent and spilled out onto the surrounding plains. The lava would have been molten when it erupted, glowing red-hot at temperatures around 900 degrees Celsius, though on Venus's surface, where the ambient temperature is already 467 degrees, the visual contrast would be less dramatic than a lava flow on Earth. The lava would have cooled and solidified over days or weeks, creating the rough, blocky texture seen in the later image. This is not the first hint of recent volcanism on Venus. Earlier studies had found localized brightening in radar images near volcanic features, which could indicate fresh, rough lava that has not yet been weathered smooth. And the European Space Agency's Venus Express mission, which orbited Venus from 2006 to 2014, detected anomalies in the infrared emission from volcanic regions, suggesting that the surface in those areas is warmer or compositionally different from the surrounding terrain, both consistent with recent lava flows. But the change detection finding is the strongest evidence yet because it shows a clear before and after difference in a short time span, ruling out long-term weathering or gradual processes. If Venus is volcanically active, the implications are profound. It means that, despite lacking plate tectonics, Venus has a mechanism to transport heat and material from its interior to the surface. That mechanism is likely mantle plumes, hot upwellings of rock that rise through the mantle and impinge on the base of the crust, melting it and creating magma that erupts at the surface. Earth has mantle plumes too. They are responsible for hotspot volcanism like Hawaii and Iceland. But on Earth, the moving tectonic plates carry the surface away from the plume, creating chains of volcanoes that record the motion of the plate. On Venus, the crust does not move, so a plume would sit in one place and create a single, long-lived volcanic complex, which is exactly what we see at Atla Regio and other highland regions. Active volcanism also means that Venus's atmosphere is being resupplied with gases from the interior. Volcanic eruptions on Earth release water vapor, carbon dioxide, sulfur dioxide, and other volatiles. On Venus, volcanic outgassing could be a significant source of sulfur dioxide, which reacts with other compounds in the atmosphere to form the sulfuric acid clouds that enshroud the planet. Sulfur dioxide has been observed to vary in concentration in Venus's atmosphere, with some measurements showing much higher levels than others, and this variability could be explained by episodic volcanic eruptions releasing fresh sulfur into the atmosphere, which is then gradually removed by chemical reactions and deposition on the surface. Understanding Venus's volcanism is not just about understanding Venus. It's about understanding how rocky planets evolve, how long they remain geologically active, and what factors determine whether a planet develops plate tectonics or remains stagnant. And with multiple new missions to Venus planned for the next decade, including orbiters with advanced radar and infrared instruments, and possibly even long-lived atmospheric balloons or surface landers, we will soon have much better data on Venus's volcanic activity, allowing us to monitor eruptions in real time and to map the distribution of fresh lava flows across the planet. 18. The dunes of Titan that defy physics. Titan, Saturn's largest moon, is the only moon in the solar system with a thick atmosphere. Thicker than Earth's, in fact, with a surface pressure 1.5 times greater than sea level on our planet. This atmosphere is mostly nitrogen, like Earth's, but with a few % methane. And it is this methane that makes Titan extraordinary. At the frigid temperatures of Titan's surface, minus 179 degrees Celsius, methane behaves the way water behaves on Earth. It exists as a gas in the atmosphere, condenses into liquid in clouds, falls as rain, collects in lakes and seas, and evaporates to complete the cycle. Titan has weather, with methane rainstorms that carve channels into the icy bedrock. It has rivers that meander across the landscape, fed by springs and runoff from the highlands. It has lakes, hundreds of them, clustered near the North Pole, with surfaces so smooth that radar bounces off them like a mirror, and some of these lakes are hundreds of meters deep, filled with liquid methane and ethane. And Titan has dunes. Vast fields of dunes near the equator, stretching for hundreds of kilometers, each dune 100 meters tall and 1 to 2 kilometers wide, marching in parallel lines like the sand dunes of the Sahara or the Namib Desert on Earth. Except these dunes are not made of sand. They are made of hydrocarbon particles, solid organic compounds that precipitate from the atmosphere and accumulate on the surface, dark and tar-like, created by photochemical reactions when sunlight breaks apart methane molecules in the upper atmosphere, and the fragments recombine into more complex molecules like ethane, propane, benzene, and long-chain polymers called tholins. But here's the problem. The dunes are oriented the wrong way. On Earth, dunes form perpendicular to the prevailing wind direction. If the wind blows from west to east, the dunes run north to south. This is basic physics. Wind picks up sand, carries it, and deposits it in ridges that lie across the wind's path. On Titan, global circulation models predict that the surface winds near the equator should blow from east to west, driven by the same Coriolis effect and Hadley cell circulation that creates trade winds on Earth. But the dunes run east to west, parallel to the predicted wind direction, as if the wind is blowing along the dunes rather than across them. This is backwards. For years, planetary scientists struggled to explain this. One possibility is that the wind models are wrong, that Titan's atmospheric circulation is more complex than we thought, and the actual surface winds blow in a different direction. But the models are based on well-established physics and have been tested against data from the Cassini-Huygens mission, which landed a probe on Titan in 2005 and deployed an orbiter that made more than 100 flybys of the Moon over 13 years, measuring wind speeds, temperature profiles, and atmospheric composition. The models match the data reasonably well at higher altitudes, so it's unlikely they are completely wrong at the surface. Another possibility is that the dunes are not formed by average winds, but by rare, strong gusts that blow in a different direction. On Earth, some dunes are shaped by storm winds rather than by the prevailing breeze. Perhaps on Titan, methane rainstorms, which occur sporadically, maybe once every few years based on observed cloud activity, generate powerful downdrafts that create winds at ground level, blowing in a direction different from the average circulation. The dune particles are also unusual. Spectroscopic measurements show they are very dark, absorbing most of the sunlight that hits them, and they are much less dense than sand, perhaps only 1/8 the density of Earth's sand grains. This means they are easier to move. They require less wind speed to lift and transport, but it also means they settle more slowly, staying suspended in the air longer. And there's another factor. Titan's atmosphere is so thick and the gravity so low, 14% of Earth's, that the terminal velocity of a falling particle is very low. A sand grain on Earth falls quickly. On Titan, a dune particle drifts lazily downward like a dust mote. This changes the dynamics of dune formation. Recent laboratory experiments and computer simulations have explored the possibility that the particles are levitated by electrostatic forces. On Titan, as on Earth, blowing wind and tumbling particles create friction, and friction generates static electricity. On Earth, this static is dissipated into the ground or neutralized by moisture in the air. But Titan's atmosphere is dry, no water vapor, and the hydrocarbon particles are excellent insulators. So the particles could accumulate significant electric charge, and charged particles repel each other. This electrostatic repulsion could lift particles off the ground, allowing them to be transported at lower wind speeds than would otherwise be required, and it could cause particles to form clumps or chains held together by electrostatic attraction between oppositely charged grains. If the particles are levitating, then the effective wind direction at the height where the particles are transported could be different from the wind direction at the surface, and this could explain the alignment of the dunes. But this is still speculative. No mission has directly measured electric fields or particle charge on Titan's surface. The truth is, we don't fully understand how Titan's dunes form, and solving this mystery will require new data, perhaps from NASA's Dragonfly mission, a rotorcraft lander scheduled to launch in 2027 and arrive at Titan in the mid-2030s, which will hop across the surface, exploring multiple sites, measuring wind speeds, sampling the dune material, and testing the properties of the particles in situ. Titan is a laboratory for studying aeolian processes, wind-driven geology, in conditions radically different from Earth, and the dunes are one of its greatest puzzles. 19. The magnetic anomaly of Ganymede. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and it holds a distinction that no other moon can claim. It has its own magnetic field, not an induced field like Europa's, created by the interaction of an external field with a conductive layer, but an intrinsic field, generated by a dynamo in its interior, just as Earth's magnetic field is generated by the churning of liquid iron in our planet's outer core. This discovery, made by NASA's Galileo spacecraft during its flybys of Ganymede in the 1990s, was unexpected. Moons are not supposed to have magnetic fields. They are too small, their interiors cool too quickly, and without the sustained heat and convection required to drive a dynamo, any magnetic field they might have generated early in their history should have died out billions of years ago. And yet, Ganymede's field persists, measured at about 750 nanoteslas at the surface, weak compared to Earth's 50,000 nanotesla field, but unmistakable and global. The field has a dipole structure, meaning it has a north pole and a south pole, aligned roughly with Ganymede's rotation axis, just like Earth's field, and it creates a magnetosphere, a bubble of magnetic influence that stands off Jupiter's powerful magnetic field and partially shields Ganymede's surface from the radiation environment of the Jovian system. This magnetosphere is tiny compared to Earth's, extending only a few Ganymede radii into space, but it is sufficient to deflect some of Jupiter's charged particles and to create Ganymede's own radiation belts, regions where particles are trapped and spiral along magnetic field lines. The existence of Ganymede's magnetic field implies something profound about its interior. There must be a layer of liquid metal convecting and generating the field through the dynamo effect, but Ganymede is an icy moon, composed of roughly equal parts rock and water ice. It does not have a large iron core like Earth or Mercury. Or does it? Gravitational measurements from Galileo, combined with models of Ganymede's internal structure, suggest that the moon is differentiated into layers, an iron-rich core at the center, surrounded by a rocky mantle, then a thick layer of high-pressure ice phases that exist only at pressures far greater than those at Earth's surface, with crystal structures denser than ordinary ice,
and finally an outer layer of more familiar ice, and possibly a subsurface ocean of liquid water, similar to Europa's ocean, but buried much deeper, perhaps 150 kilometers below the surface. If this model is correct, then Ganymede's core is about half the radius of the Moon, roughly 800 kilometers across, and at least part of it must still be liquid. The temperature at the core is estimated to be around 1500 Kelvin, hot enough to keep iron molten despite the immense pressures. But why hasn't the core
solidified over 4.5 billion years? What is keeping Ganymede's interior warm? The answer, as with so many mysteries in the outer solar system, may be tidal heating. But the story is more complicated than on Europa or Enceladus. Ganymede is part of a resonance with Io and Europa, the same Laplace resonance that keeps Europa's orbit eccentric and drives intense tidal heating on Io. Ganymede's orbit is also slightly eccentric due to this resonance, and the tidal forces from Jupiter flex the Moon's interior, generating heat. But Ganymede is farther from Jupiter than Europa, so the tidal forces are weaker, and models suggest that tidal heating alone cannot explain the heat required to keep the core molten. There may be additional heat sources: radioactive decay of long-lived isotopes like uranium, thorium, and potassium in the rocky mantle, residual heat from Ganymede's formation, trapped in the deep interior by the insulating layers of ice, or heat released by the gradual crystallization of the core as the outer parts of the iron core solidify and release latent heat, driving convection in the remaining liquid. Whatever the combination of heat sources, the fact remains: Ganymede has a dynamo, and it has been active for a long time, possibly for most of the Moon's history. And this dynamo has consequences beyond just creating a magnetic field. It implies that Ganymede's interior is dynamic, with convection currents flowing, material mixing, and possibly even differentiation still ongoing. It suggests that Ganymede, despite being a moon and despite orbiting in the frozen outer solar system, has an interior that, in some ways, resembles a small planet more than a passive chunk of ice and rock. The magnetic field also has implications for Ganymede's tenuous atmosphere. Ganymede has an exosphere, an incredibly thin atmosphere, barely more than a vacuum, composed mostly of oxygen. This oxygen is not breathed out by life. It is created by radiolysis, the process by which high-energy particles from Jupiter's magnetosphere strike the ice on Ganymede's surface, break apart water molecules, and release oxygen and hydrogen. The hydrogen escapes to space, being too light to be held by Ganymede's weak gravity, but the oxygen lingers, forming a sparse cloud around the Moon. And within this oxygen exosphere, there are auroras. The Hubble Space Telescope has observed them in ultraviolet light, glowing regions near Ganymede's magnetic poles, where charged particles from Jupiter's magnetosphere funnel along Ganymede's magnetic field lines and collide with oxygen atoms, exciting them and causing them to emit UV photons. These auroras are not visible to the human eye, but they are there, faint curtains of light dancing above a frozen landscape, driven by the interaction of two magnetic fields, Jupiter's and Ganymede's, locked in a perpetual electromagnetic tug-of-war. NASA's Juno spacecraft, during extended flybys of Ganymede in 2021, measured the magnetic field with much higher precision than Galileo could, mapping the field's structure in 3 dimensions and confirming that it is indeed a dipole field, though with some asymmetries that hint at complexities in the dynamo process. And the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023 and scheduled to arrive at Jupiter in 2031, will spend years studying Ganymede, eventually entering orbit around the Moon.
and conducting detailed surveys of the magnetic field, the interior structure, and the surface composition. JUICE will carry ice-penetrating radar to probe the subsurface ocean, a magnetometer to map the field at high resolution, and spectrometers to study the composition of the exosphere and the surface ice. And perhaps, with all this new data, we will finally understand why Ganymede, alone among moons, still generates its own magnetic field, and what this tells us about the thermal and chemical evolution of large icy bodies in the solar system.
20. The Cryovolcanoes of Ceres. Ceres was the first asteroid ever discovered, spotted by Giuseppe Piazzi on the first night of the 19th century, January 1st, 1801. And for decades, it was classified as a planet, then demoted to asteroid, and finally, in 2006, promoted again to the new category of dwarf planet, joining Pluto in the ranks of bodies massive enough to be rounded by their own gravity, but not massive enough to clear their orbits of other debris. Ceres orbits in the asteroid belt between Mars and Jupiter, a region we imagine as dry and dead, populated by tumbling rocks, the leftover rubble from the formation of the solar system, fragments that never accreted into a planet. But Ceres is no dry rock. It is a water world. About 25% of its mass is water ice mixed with rock and possibly salts, and beneath its battered exterior lies something extraordinary, a subsurface ocean, or at least pockets of liquid water trapped in the crust, kept from freezing by a combination of residual heat from formation, radioactive decay, and possibly tidal interactions with Jupiter's distant gravitational influence. And where there is liquid water interacting with rock, there is the possibility of volcanism. Not the silicate volcanism of Earth or Venus, where molten rock erupts at temperatures of 1,000 degrees or more, but cryovolcanism, ice volcanism, where the magma is a slurry of liquid water, brine, and perhaps ammonia or other antifreeze compounds that lower the freezing point and allow the liquid to flow even in the frigid conditions of the outer solar system. The evidence for cryovolcanism on Ceres comes from NASA's Dawn spacecraft, which orbited the dwarf planet from 2015 to 2018, mapping its surface in exquisite detail. The most striking feature is Ahuna Mons, a mountain 4 kilometers high and 17 kilometers wide at the base, rising from the relatively flat plains of Ceres like a giant blister. Ahuna Mons is smooth compared to the surrounding terrain, with flanks that slope gently upward and a summit that is fractured and collapsed in places, as if something once pushed up from below and then drained away. Its shape is unlike impact craters or tectonic features. It is a dome, and domes on rocky bodies are typically volcanic constructs, built by the slow extrusion of viscous lava. But on Ceres, the lava is not molten rock. Spectroscopic analysis of Ahuna Mons shows that its surface is bright and rich in carbonates, minerals that form when carbon dioxide reacts with water in the presence of rock. This composition is consistent with cryovolcanic material, a mixture of ice, salts, and minerals brought up from the interior. And age estimates based on crater counting suggest that Ahuna Mons is geologically young, perhaps only 200 million years old, recent enough that in the context of Ceres's 4.5 billion year history, it might as well have formed yesterday. But Ahuna Mons is not alone. Dawn's cameras reviewed other promising cryovolcanic features, including Okator crater, an impact crater 92 kilometers across that contains the brightest features on Ceres. At the center of Okator is a pit, Cerealia Facula, and within the pit is a mound of bright, reflective material that appears to have oozed up from below and pooled on the crater floor. This material is not ice in the form we are familiar with. Spectroscopy shows it is a mixture of sodium carbonate, ammonium chloride, and water ice. Essentially, salty ice. The residue of briny water that reached the surface evaporated and left its salts behind. The impact that created Okator happened about 20 million years ago, and the cryovolcanic activity appears to be even more recent. Fresher, less degraded deposits within the central pit suggest that brine was seeping to the surface as recently as a few million years ago, and possibly even more recently. Dawn detected faint water vapor emissions from Okator crater, hinting that sublimation, ice turning directly to vapor, or possibly even active seepage is still occurring, though at such a low rate that it is barely detectable. This is profound. Ceres, a dwarf planet in the asteroid belt, a body we thought of as ancient and inert, has been geologically active within the last few million years and may still be active today. The discovery of a subsurface ocean on Ceres was confirmed by gravity measurements. Dawn orbited Ceres at different altitudes, and by measuring the tiny perturbations in its orbit caused by Ceres's gravity field, scientists were able to map the distribution of mass within the dwarf planet. The data showed that Ceres is less dense in its outer layers than expected if it were solid rock and ice all the way through, and the best explanation is a layer of liquid or partially liquid brine extending from about 40 kilometers depth down to the rocky core. This ocean is not a single planet-wide reservoir like Europa's ocean. It is probably patchy, with pockets and lenses of brine trapped in the crust, connected by fractures and conduits. But it is there, and it has been there long enough to drive cryovolcanism to the surface. The mechanism is thought to be similar to terrestrial volcanism. Brine, being less dense than the solid ice around it, rises buoyantly through cracks in the crust. As it rises, the pressure decreases, and dissolved gases, perhaps carbon dioxide or methane, come out of solution, creating bubbles that further drive the ascent. When the brine reaches the surface, it erupts gently. No explosive eruptions like those on Io or Enceladus, but slow, effusive flows that build domes and mounds over thousands of years. And then, exposed to vacuum and the cold of space, the water evaporates or freezes, leaving behind the salts and carbonates that Dawn observed. The discovery that Ceres has cryovolcanism and a subsurface ocean raises the tantalizing possibility that it could harbor life. Where there is liquid water, organic molecules, and energy from geological processes, there is the potential for chemistry to cross the threshold into biology. Ceres is not as promising as Europa or Enceladus. It is farther from the Sun, colder, and its ocean is probably more isolated. But it is accessible, orbiting in the asteroid belt rather than deep in the outer solar system. A future mission to Ceres could land near Ahuna Mons or Akator crater, drill into the crust, sample the briny deposits, and search for organic molecules or biosignatures. And that mission might answer the question, is Ceres merely a geologically interesting dwarf planet, or is it a harbor for life hiding in plain sight between Mars and Jupiter? 21. Uranus, the planet tilted on its side. Uranus is broken. Or at least, that is what it looks like. Every other planet in the solar system spins more or less upright, with their rotation axes tilted by modest angles relative to the plane of their orbits. Earth is tilted 23.5 degrees, which gives us our seasons. Mars is tilted 25 degrees. Jupiter barely tilts at all, at just 3 degrees. But Uranus is tilted 98 degrees. Its rotation axis lies almost in the plane of its orbit, meaning the planet rotates on its side, rolling around the Sun like a barrel rather than spinning like a top. During Uranus's 84-year orbit, each pole spends 42 years in continuous sunlight and 42 years in continuous darkness. The northern hemisphere experiences a summer that lasts an entire human lifetime, followed by a winter equally long. The equator, which on every other planet receives the most sunlight on average, is one of the coldest regions on Uranus because it receives only glancing sunlight during most of the orbit, with the sun rising and setting once per day as Uranus rotates. This is a completely alien climate regime, unlike anything else in the solar system, and it creates atmospheric dynamics that are only beginning to be understood. The question is, how did Uranus end up tilted this way? Planets form with the angular momentum of the protoplanetary disk, which means they should all spin in the same direction and with similar tilts. A tilt of 98 degrees is not a natural outcome of planet formation. It is evidence of something violent, something catastrophic. The leading hypothesis is a giant impact. Early in the history of the solar system, when planets were still forming and the inner regions were crowded with protoplanets and large planetesimals, collisions were common. Uranus, forming in the outer solar system, where material was more spread out and collisions less frequent, might have been struck late in its formation by a protoplanet roughly the size of Earth. Such an impact, delivered at the right angle and velocity, could have knocked Uranus onto its side, transferring enough angular momentum to flip the rotation axis by 90 degrees. Computer simulations of such impacts show that it is possible, but the details matter. The impactor needs to be large enough to deliver the necessary momentum, but not so large that it destroys Uranus or ejects so much material that the planet's mass is significantly reduced. And the impact needs to occur late enough in Uranus's formation that the planet has already accreted most of its mass and differentiated into a core and envelope, but early enough that the heat from the impact can be radiated away over geological time. But there is a problem with the giant impact hypothesis: Uranus's moons. Uranus has 27 known moons, and the 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, all orbit in the plane of Uranus's equator, which is also the plane perpendicular to the rotation axis. If Uranus were knocked onto its side by a giant impact, you would expect the moons to orbit in the plane of the solar system, the plane in which the impact occurred, not in the new equatorial plane of the tilted planet. The fact that the moons orbit in the equatorial plane suggests they formed after the tilt, from the debris of the impact itself, similar to how Earth's moon is thought to have formed from the debris of the giant impact that struck Earth. But if the moons formed from impact debris, they should be compositionally distinct from Uranus's bulk composition, enriched in material from the impactor. We do not have detailed compositional data for Uranus's moons. Only Voyager 2 has visited the system, and it did not carry the instruments needed for detailed compositional analysis. But the limited data we have suggest the moons are typical icy bodies, similar in composition to other moons in the outer solar system. This does not rule out the giant impact hypothesis, but it complicates it. Perhaps the impactor had a composition similar to Uranus, or perhaps the moons that existed before the impact were destroyed, and the current moons formed later from a disk of debris that settled into the new equatorial plane. Or perhaps the tilt was not caused by a single giant impact, but by a series of smaller impacts, each nudging the rotation axis until it reached its current extreme orientation. Some recent models suggest that a grazing collision, an impact where the protoplanet did not strike head-on, but instead skimmed Uranus's outer layers, could tilt the planet without ejecting massive amounts of material. And such a collision might preserve or even create the current system of moons. The extreme tilt has consequences beyond just unusual seasons. Uranus's magnetic field is also strange. Most planets with magnetic fields have dipole fields aligned roughly with their rotation axes. Earth's magnetic north pole is close to the geographic north pole, and Jupiter's and Saturn's fields are similarly aligned. But Uranus's magnetic field is tilted 59 degrees away from its rotation axis and offset from the center of the planet, as if the dynamo generating the field is not in the core, but in a shell surrounding the core. This is bizarre and not fully understood. One possibility is that Uranus's interior is layered in an unusual way, with the conducting fluid that generates the field confined to a relatively thin shell at intermediate depths, rather than filling the entire outer core. Another possibility is that the magnetic field is in the process of reversing, as Earth's field has done many times in geological history, and we are observing it in a transitional state. But without more data, this is speculation. Voyager 2's flyby of Uranus in 1986 was brief, just a few days of close observation, and no other spacecraft has returned. There are proposals for a Uranus orbiter mission, which would spend years studying the planet, its rings, its moons, and its magnetic field, and such a mission is considered a high priority by the planetary science community. When that mission finally arrives, perhaps in the 2040s or 2050s, we will have the opportunity to study this tilted world in detail and to unravel the history written in its spin. 22. The mysterious blue of Neptune. Neptune and Uranus are twins, or at least they should be. They are nearly identical in size. Neptune is only slightly smaller than Uranus, and they have similar masses, similar densities, and similar compositions. Both are ice giants, a category distinct from the gas giants, Jupiter and Saturn, composed primarily of water, methane, and ammonia ices surrounding relatively small, rocky cores, with atmospheres of hydrogen and helium making up only about 15 to 20% of their mass. Spectroscopic measurements show that both planets have methane in their upper atmospheres, and it is this methane that gives them their blue color. Methane absorbs red light and reflects blue, so when sunlight strikes the atmosphere, the red wavelengths are absorbed and the blue wavelengths are scattered back to space, reaching our telescopes and our eyes. But here is the mystery. Neptune is a much deeper, richer blue than Uranus. Uranus appears as a pale cyan, almost greenish blue, a muted color like a robin's egg left out in the sun. Neptune, by contrast, is a vibrant azure, a saturated blue that looks almost painted on, more vivid than the blue of Earth's oceans or sky. And yet, spectroscopic measurements show that Uranus actually has slightly more methane in its upper atmosphere than Neptune. If methane is what makes them blue, Neptune should be paler, not darker. So why is Neptune so blue? This question has puzzled planetary scientists for decades. The simple answer, that Neptune has more methane, does not work. There must be something else in Neptune's atmosphere, some additional component that enhances the blue color, either by absorbing red light more efficiently or by scattering blue light more effectively. One possibility is that Neptune has a higher concentration of haze particles in its stratosphere, tiny aerosols, perhaps composed of hydrocarbons or other photochemical products formed when ultraviolet light from the sun breaks apart methane molecules and the fragments recombine into more complex compounds. These haze particles, depending on their size and composition, could preferentially scatter blue light, intensifying the color. Observations from the Hubble Space Telescope and ground-based telescopes equipped with adaptive optics have revealed that both Uranus and Neptune have haze layers, but the hazes appear different. Uranus's haze is thicker and more opaque, creating a milky, diffuse appearance that washes out the color. Neptune's haze is more transparent, allowing the deeper blue of the methane-rich atmosphere to show through, while adding its own contribution to the scattering. But the exact composition and structure of these hazes remain uncertain. Spectroscopy can identify molecules based on their absorption features, but haze particles do not have sharp absorption lines. They produce broad, featureless extinction that is difficult to interpret without knowing the particle size distribution and refractive index. Another possibility involves the vertical structure of the atmosphere. Neptune is more dynamically active than Uranus. It has the fastest winds in the solar system, with storms and cloud features that appear, evolve, and disappear on timescales of weeks to months. The Great Dark Spot, a storm system larger than Earth, was observed by Voyager 2 in 1989 and had vanished by the time Hubble observed Neptune in 1994. New dark spots have appeared since, and bright companion clouds, high-altitude methane ice clouds that form in the updrafts associated with these storms, are frequently seen. Uranus, by contrast, is much more placid, with fewer visible storms and a more uniform appearance. This difference in atmospheric activity could affect the distribution of methane and haze particles. If Neptune's vigorous convection and strong winds are constantly lofting fresh methane from deeper levels to the upper atmosphere, or if they are mixing haze particles in a way that enhances blue scattering, this could explain the color difference. But again, the details are murky, and without in situ measurements, probes that descend into the atmospheres and measure composition, temperature, and particle properties directly, we are limited to remote observations that can only constrain the surface layers. There is also the possibility of an unknown atmospheric constituent. Spectroscopy is powerful, but it can only detect molecules that have strong absorption features in the wavelengths we observe. If there is a compound in Neptune's atmosphere that absorbs red light but has no obvious spectral signature, or has features that are blended with other, more abundant molecules, it could be hiding in plain sight. Some researchers have speculated about organic compounds, sulfur compounds, or even exotic ices that could contribute to the color, but these are largely guesses without direct evidence. What is clear is that Neptune's color is not fully explained by our current models, and solving this mystery will require better data. The last close-up observations of Neptune were from Voyager 2's flyby in 1989, 36 years ago. Since then, we have relied on telescopes observing from Earth orbit or from the ground. And while these observations have revealed much about Neptune's atmosphere, its winds, its storms, its seasonal changes as different hemispheres tilt toward the Sun over Neptune's 165-year orbit, they cannot match the detail and precision of a dedicated mission. There are proposals for a Neptune orbiter, similar to the proposed Uranus orbiter, which would carry advanced spectrometers, cameras, and atmospheric probes to study the planet in unprecedented detail. Such a mission could finally answer the question of why Neptune is so blue, and in doing so, it would reveal something deeper about the chemistry and physics of ice giant atmospheres, knowledge that applies not just to Neptune, but to the thousands of similar planets we are now discovering around other stars. Exoplanet surveys have found that ice giants are common in the galaxy, perhaps even more common than gas giants like Jupiter. And many of these distant worlds may resemble Neptune or Uranus. Understanding Neptune's color is not just about aesthetics. It is about understanding a whole class of planets that may be among the most numerous in the universe. 23. The Great Dark Spot that appears and vanishes. When Voyager 2 arrived at Neptune in August 1989, completing its grand tour of the outer solar system after visiting Jupiter, Saturn, and Uranus, it discovered something unexpected: a storm. Not just any storm, but a massive anticyclonic vortex roughly the size of Earth, swirling in Neptune's southern hemisphere at a latitude of about 22 degrees south. The storm was dark,
absorbing sunlight rather than reflecting it, which made it stand out against the brighter surrounding clouds. It was immediately dubbed the Great Dark Spot, in homage to Jupiter's Great Red Spot, though the two phenomena are quite different. Jupiter's Great Red Spot is reddish and has persisted for at least 350 years, possibly much longer, making it the longest-lived storm known in the solar system. Neptune's Great Dark Spot, by contrast, was a fleeting thing. Voyager observed it for only a few months as the spacecraft approached and then flew past Neptune, capturing images and data that showed the storm rotating counterclockwise and drifting slowly westward relative to Neptune's interior rotation. The storm had structure: a dark core, bright companion clouds at its edges, methane ice crystals condensing in the cold updrafts at the storm's periphery, and an irregular shape that changed from day to day. Then Voyager left, continuing on its trajectory out of the solar system, and for 5 years Neptune was unobserved except by distant ground-based telescopes that could see only a small, featureless blue disk. In 1994, the Hubble Space Telescope, newly repaired and equipped with optics that could finally resolve features on Neptune's surface, turned its cameras toward the planet. Astronomers expected to see the Great Dark Spot, still churning away in the southern hemisphere. But it was gone, completely absent. The region where the storm had been was now featureless, indistinguishable from the surrounding atmosphere. The Great Dark Spot had disappeared. This was a shock. Storms on Earth can last days or weeks, occasionally months if they are hurricanes over warm oceans, but they always dissipate eventually. Storms on Jupiter, however, are extraordinarily long-lived, with the Great Red Spot having raged for centuries and smaller storms persisting for decades. Neptune, it seemed, fell somewhere in between. Its storms were large and powerful, but not permanent. Over the following years, Hubble continued to monitor Neptune, and it found new dark spots appearing in different locations. One in the northern hemisphere in 1994, another in the southern hemisphere in 2015, and yet another in 2018. Each spot appeared, persisted for months or a few years, and then faded away. Some spots drifted toward the equator before vanishing, while others simply dissipated in place. The mechanism behind this appearance and disappearance remains one of Neptune's great mysteries. Dark spots on Neptune are thought to be high-pressure anticyclonic vortices, similar in structure to Jupiter's storms. The darkness is not due to the storm being intrinsically dark, but rather due to the absence of high-altitude haze. Normally, Neptune's atmosphere is covered with a layer of photochemical haze that reflects sunlight and gives the planet its bright appearance. But in the center of an anticyclone, air is descending, and as it descends, it warms and compresses, causing haze particles to evaporate or simply pushing them downward out of the visible layer. This creates a window through which we can see deeper into the atmosphere, to levels where methane absorbs more light, making the region appear dark. The bright companion clouds at the edges of the dark spots are formed by methane ice crystallizing in the upwelling air at the storm's periphery, similar to the high-altitude cirrus clouds that form around terrestrial hurricanes. But why do these storms form in the first place? And why do they disappear? On Earth, hurricanes are powered by the release of latent heat when water vapor condenses into rain. Essentially, they are heat engines that convert the energy stored in warm ocean water into kinetic energy of wind. On Jupiter, the Great Red Spot is thought to be powered by heat rising from the planet's deep interior, combined with the planet's rapid rotation and the jet streams that constrain the storm's movement. Neptune's internal heat source is even more pronounced than Jupiter's. Neptune radiates about 2.6 times more energy than it receives from the Sun, a higher ratio than any other planet except Jupiter. This internal heat drives convection in the atmosphere, creating updrafts and downdrafts, and these convective cells could spawn storms.
But Neptune also rotates relatively quickly, about 16 hours per rotation, which creates strong Coriolis forces that organize atmospheric flows into jet streams and vortices. One hypothesis for the disappearance of Neptune's dark spots is meridional drift. The storms drift toward the equator, and as they approach the equator, the Coriolis force weakens. The Coriolis effect is zero at the equator, which destabilizes the vortex and causes it to dissipate. Observations support this to some extent. The 1989 Great Dark Spot was observed drifting slowly toward the equator, and some of the later spots also showed equatorward drift. But not all of them. Some disappeared without significant latitudinal movement. Another possibility is that the storms are simply torn apart by wind shear. Neptune's atmosphere has multiple jet streams at different latitudes, flowing at different speeds, and a storm caught between two jets would experience shearing forces that could stretch and disrupt it. Or perhaps the storms run out of energy, their internal heat dissipating through radiation to space, and without a continuous energy source, they collapse and fade. The truth is, we do not know. Neptune's atmosphere is under-observed.
Voyager 2's flyby provided a snapshot, a single moment in time. Hubble and ground-based telescopes provide occasional follow-up observations, but they are limited by resolution and by the availability of telescope time. What is needed is a dedicated Neptune mission, an orbiter that would spend years observing the planet continuously, tracking storms from formation to dissipation, measuring wind speeds, temperature profiles, and atmospheric composition as a function of depth and latitude. Such a mission would transform our understanding of Neptune and, by extension, of atmospheric dynamics on ice giants everywhere.
24. Pluto, the frozen heart. Pluto was supposed to be simple. A frozen, dead world at the edge of the solar system, pockmarked with craters from 4.5 billion years of impacts. Geologically inert, a relic of the early solar system preserved in deep freeze. This was the expectation when NASA's New Horizons spacecraft, launched in 2006, began its 9.5-year journey to the Kuiper belt. But when New Horizons arrived at Pluto in July 2015, speeding past at 50,000 kilometers per hour and capturing images and data during a single intense flyby, it revealed a world that defied every expectation. The most striking feature, visible from millions of kilometers away as New Horizons approached, was a heart. Not a metaphorical heart, but a vast, bright, heart-shaped region on Pluto's surface, informally named Tombaugh Regio after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. The heart is divided into two lobes. The western lobe, Sputnik Planitia, is a smooth, crater-free plain of nitrogen ice, 1,000 kilometers across, brighter than any other region on Pluto. It shows no impact craters, none of the scars that mark every other ancient surface in the solar system, which means it is young, geologically active within the last 10 million years, possibly within the last 100,000 years. This is extraordinary. Pluto is tiny, only 2/3 the diameter of Earth's moon, and it is so far from the sun that sunlight provides negligible heating. It should have cooled off and frozen solid billions of years ago. And yet here is Sputnik Planitia, a region resurfaced so recently that it might as well be happening now. Sputnik Planitia is not just smooth, it is patterned. High-resolution images from New Horizons show that the plain is divided into polygonal cells, each about 10 to 40 kilometers across, separated by shallow troughs. These cells are convection cells, analogous to the convection cells in a pot of boiling water or in Earth's mantle, but made of solid nitrogen ice. Nitrogen ice on Pluto is not like the ice in your freezer. At Pluto's surface temperature of -223 degrees Celsius, nitrogen ice is near its melting point, or rather, near the temperature where it becomes plastic and can flow over geological timescales. The cells form because the ice at the surface is slightly colder than the ice below, creating a density inversion. The warmer, less dense ice rises in the center of each cell, spreads outward, cools, and sinks at the edges, creating a slow, churning motion. The timescale for one convection cycle is estimated to be about 500,000 years, faster than the convection in Earth's mantle, which takes hundreds of millions of years, but still slow by human standards. Yet this motion is fast enough to erase craters. Any impact that occurs on Sputnik Planitia is gradually buried and smoothed over by the convecting ice, which is why the plane appears so pristine. The nitrogen ice is several kilometers thick, possibly tens of kilometers, and it fills a deep basin that may be an ancient impact crater, one of the largest in the solar system, though its origin is debated. The ice is also slightly heavier on one side of Pluto, creating a gravitational anomaly, an excess of mass that has reoriented Pluto over geological time so that Sputnik Planitia now sits almost exactly on the equator facing Charon, Pluto's largest moon. This is not a coincidence. The extra mass acts like a weight on a spinning top, causing Pluto to tip until the mass is aligned with the tidal axis defined by Charon's gravity. But Sputnik Planitia is only part of Pluto's story. The rest of the planet is equally strange and equally active. To the west of the plane are mountains, water ice mountains, because water ice at Pluto's temperatures is as hard as rock and can support topography. These mountains rise 3 to 4 kilometers above the surrounding terrain, as tall as the Rockies or the Alps on Earth, with steep, rugged slopes that suggest they are young, not yet eroded smooth. The presence of mountains so close to Sputnik Planitia, which is clearly geologically active, suggests that the entire region has been reshaped recently, possibly by tectonic forces related to the convection and motion of the nitrogen ice. To the south of Sputnik Planitia is a region of strange, blade-like ridges composed of methane ice, aligned north-south and rising hundreds of meters tall, unlike any landform on Earth. These ridges, called penitentes, in analogy to similar but much smaller features found in high-altitude deserts on Earth, are thought to form by differential sublimation. Methane ice evaporates more slowly in the troughs than on the peaks, causing the ridges to grow over millions of years. And to the east of Sputnik Planitia is Cthulhu Macula, a vast, dark region covered with reddish-brown organic compounds called tholins, created when ultraviolet light from the sun strikes methane in Pluto's thin atmosphere and breaks it apart, allowing the carbon and hydrogen to recombine into complex molecules that drift down and coat the surface. Cthulhu is ancient, heavily cratered, and it provides a stark contrast to the youthful Sputnik Planitia. Two terrains side by side, one frozen in time, the other constantly renewing itself. Pluto also has an atmosphere, though calling it an atmosphere is generous. The surface pressure is about 10 microbars, 100,000 times thinner than Earth's atmosphere, barely more than a hard vacuum. But this atmosphere is dynamic. It is composed mostly of nitrogen, with traces of methane and carbon monoxide, and it extends hundreds of kilometers above the surface, far higher than Earth's atmosphere relative to the planet's size. This is because Pluto's gravity is so weak, only 6% of Earth's gravity, that atmospheric gases are barely held down. The atmosphere is also escaping. Pluto loses about 500 tons of atmosphere per hour to space. Nitrogen molecules drifting away into the Kuiper belt, never to return. and the atmosphere varies with Pluto's orbit. Pluto's orbit is highly elliptical, and when Pluto is closest to the Sun, the surface warms slightly, causing nitrogen and methane ices to sublimate and thicken the atmosphere. When Pluto moves farther from the Sun, the atmosphere cools and freezes out, snowing back onto the surface. New horizons arrived just after Pluto's closest approach to the Sun, so the atmosphere was relatively thick, and the spacecraft was able to measure its structure and composition in detail using radio occultation, watching how radio signals bent as they passed through the atmosphere. The results showed layers, temperature inversions, and haze. Multiple layers of haze particles suspended in the atmosphere, probably tholins and other photochemical products, giving Pluto a blue tinge when viewed in backlit images. Pluto, the frozen dwarf planet at the edge of the solar system, has blue skies.
25. Charon,
The moon that dances with Pluto. Charon is not a typical moon. Most moons orbit their planets at a respectful distance, held by gravity, but clearly subordinate, smaller and less massive, circling the larger body in the same way that planets orbit the Sun. But Charon is different. Charon is half the diameter of Pluto and 1/8 its mass, making it by far the largest moon relative to its planet in the solar system. Earth's moon is large compared to Earth, about 1/4 the diameter and 1/80th the mass. But Charon takes this to an extreme. The mass ratio is so close to unity that Pluto and Charon do not orbit each other in the traditional sense. Instead, they orbit a common center of mass, a point in space called the barycenter, which lies not inside Pluto, but in the space between the two bodies, about 900 kilometers above Pluto's surface. This makes the Pluto-Charon system a binary dwarf planet, two worlds locked in a gravitational dance, forever facing each other, rotating and revolving in perfect synchrony every 6.4 Earth days. If you stood on the surface of Pluto, Charon would hang motionless in the sky, never rising, never setting, fixed above the same spot on the horizon for eternity. And if you stood on Charon, Pluto would do the same, a giant icy sphere suspended in the black, unchanging. This is mutual tidal locking, and it is the ultimate fate of any close binary system given enough time. Tidal forces gradually synchronize the rotations until both bodies show the same face to each other, and the system reaches a state of minimum energy. How did Charon form? The leading theory, supported by simulations and by the physical characteristics of the Pluto-Charon system, is a giant impact, similar to the hypothesis for the formation of Earth's moon. Early in the history of the solar system, when Pluto and other Kuiper belt objects were still forming from the aggregation of smaller planetesimals, Pluto was struck by another large body, perhaps a third to half Pluto's mass. The impact was not head-on, but oblique, a glancing blow that shattered both bodies and ejected a spray of debris into orbit around what remained of Pluto. This debris, composed of ice and rock from the mantles of both the impactor and Pluto, would have quickly coalesced, within a few thousand years, into a large moon orbiting close to Pluto. That moon was Charon. Over tens of millions of years, tidal forces acted on both Pluto and Charon, dissipating energy through internal friction and causing Charon's orbit to expand, while simultaneously slowing Pluto's rotation and locking Charon's rotation to its orbit. Eventually, the system reached the stable, mutually locked configuration we see today. The giant impact hypothesis explains several features of the system. The large size of Charon, the fact that Charon's density is lower than Pluto's, suggesting Charon is composed of more ice and less rock, consistent with it being formed from mantle material
rather than core material. And the fact that Pluto's rotation axis is tilted 120 degrees, lying almost on its side, similar to Uranus. Such a tilt is not a natural outcome of planet formation, but is consistent with a major collision that imparted angular momentum in an unusual direction. When New Horizons flew past Charon in 2015, it revealed a surface that was, like Pluto's, far more complex and geologically interesting than expected. Charon's most prominent feature is a vast, dark red region covering its north polar cap, informally named Mordor Macula. This dark material is thought to be tholins, complex organic molecules created by the irradiation of methane and nitrogen ices. But the curious thing is that these tholins did not form on Charon itself. Charon's gravity is too weak to hold a significant atmosphere, and without an atmosphere, there is no methane to be broken down by ultraviolet light. Instead, the tholins are hijacked from Pluto. Pluto's escaping atmosphere, nitrogen and methane molecules drifting away into space, is partially captured by Charon's gravity. The methane freezes out on Charon's cold surface, particularly at the poles where it is coldest and where sunlight is weakest. Over millions of years, this methane is irradiated by ultraviolet light and by charged particles from the solar wind, converting it into reddish-brown tholins that darken the polar cap. Charon, in a sense, is being painted by Pluto's atmosphere, a slow accumulation of color transferred from one world to another across the vacuum of space. But the most surprising discovery on Charon was not the dark polar cap, it was the evidence of recent geological activity. The southern hemisphere, which New Horizons imaged in detail, is relatively smooth and lightly cratered, suggesting it has been resurfaced within the last few billion years. And cutting across this terrain are enormous chasms, fault systems, some of them deeper than the Grand Canyon and longer than the continental United States is wide. The largest of these, named Serenity Chasma, stretches for more than 1,800 kilometers and plunges 7 to 9 kilometers deep. These chasms are extensional features, formed when Charon's crust was pulled apart, and they indicate that Charon expanded at some point in its history. The most likely explanation is that Charon once had a subsurface ocean, a layer of liquid water, perhaps mixed with ammonia to lower the freezing point, lying beneath the outer ice shell. As this ocean gradually froze over hundreds of millions of years, the water expanded. Water ice is less dense than liquid water, and the expansion cracked the crust, creating the enormous chasms we see today. The fact that these features are so large and so well preserved suggests the freezing occurred relatively recently, perhaps within the last billion years, and possibly much more recently. There is also evidence of cryovolcanism. In one region, a mountain with a summit depression, possibly a cryovolcanic caldera, sits near a smooth plain that may be a frozen lake of water or ammonia water slush that erupted from the interior. The colors in this region are different from the surrounding terrain, with more reds and blues, suggesting compositional differences consistent with material brought up from depth. Charon, despite being a small, distant moon orbiting a dwarf planet in the frozen Kuiper belt, was once geologically active, and that activity may have ceased only recently in geological terms. The heat required to maintain a subsurface ocean and drive cryovolcanism could have come from radioactive decay of long-lived isotopes like potassium, uranium, and thorium in Charon's rocky core, or from tidal heating during an earlier epoch when Charon's orbit was still eccentric and not yet fully circularized. Once the orbit became circular and the tidal heating ceased, the ocean would have begun to freeze, and Charon would have entered the frozen, geologically quiet state it is in today. Or so we think.
Without a dedicated mission to return to Pluto and Charon, without instruments to measure seismic activity or heat flow or subsurface structure with radar, we cannot be certain. Charon may still hold surprises, hidden beneath its icy crust, waiting to be discovered.
26. The Kuiper Belt and the frozen worlds beyond Neptune, where sunlight is so faint that the sun appears as little more than a very bright star, lies a vast region of icy debris known as the Kuiper Belt. It begins at about 30 astronomical units from the Sun, 30 times the Earth-Sun distance, and extends outward to about 50 astronomical units, possibly farther. This is a region we are only beginning to explore, a frontier where our spacecraft have barely ventured and our telescopes strain to see. The Kuiper Belt is populated by millions, perhaps billions of objects. Icy bodies composed primarily of frozen water, methane, ammonia and nitrogen, mixed with rock and organic compounds. These are the remnants of the protoplanetary disk, the leftover building blocks from the formation of the solar system that never accreted into a planet. In the inner solar system, these building blocks were swept up by the rocky planets or ejected by gravitational interactions with Jupiter. But here, beyond Neptune, they remain, preserved in cold storage for 4.5 billion years. The Kuiper Belt is a fossil record, a window into the early solar system, and studying it tells us not just about the history of our own planetary system, but about the process of planet formation everywhere in the galaxy. The existence of the Kuiper Belt was predicted long before it was observed. In 1951, astronomer Gerard Kuiper speculated that there should be a belt of icy debris beyond Neptune, left over from the formation of the planets, though he thought it would be empty now, cleared out by gravitational perturbations from the giant planets. In the 1980s, computer simulations of solar system formation showed that such a belt should not only exist, but should still be populated with objects, and that some of these objects would occasionally be perturbed into the inner solar system, becoming short-period comets, comets with orbital periods of less than 200 years, like Halley's Comet. The Kuiper Belt, the models suggested, was the source of these comets. But observational confirmation was slow to come. The objects in the Kuiper Belt are small and dark, reflecting very little sunlight, and even the largest of them, Pluto, which we now classify as a Kuiper Belt object, is barely visible as a dot of light in all but the most powerful telescopes. But in 1992, astronomers David Jewett and Jane Liu, after 5 years of systematic searching, discovered the first confirmed Kuiper Belt object other than Pluto, a small icy body about 250 kilometers across, designated 1992 QB1. This was the breakthrough. Within a few years, hundreds more were found, and today we know of more than 2,000 Kuiper Belt objects, with new ones discovered every year as survey telescopes scan the sky. The Kuiper Belt is not uniform. It has structure, subpopulations of objects with different orbital characteristics. There are classical Kuiper Belt objects which orbit in low eccentricity, low inclination orbits between 40 and 50 astronomical units, relatively undisturbed by Neptune. There are resonant objects which are locked in orbital resonances with Neptune, the most famous being the Plutinos, objects like Pluto that orbit twice for every 3 times Neptune orbits, a 3-to-2 resonance that protects them from close encounters with the giant planet. There are scattered disk objects, which have highly eccentric and inclined orbits, evidence that they were gravitationally scattered by Neptune and flung into the outer reaches of the solar system. And there are detached objects, which orbit so far from the Sun and with such high perihelia, closest approaches to the Sun, that they could not have been scattered by Neptune's current orbit. These objects, like Sedna, which has a perihelion of 76 astronomical units and an aphelion of 936 astronomical units, taking 11,000 years to complete one orbit, are perhaps the most mysterious. What could have placed them in such distant, detached orbits?
Possibilities include a close encounter with a passing star billions of years ago, gravitational influence from a yet undiscovered distant planet, the hypothetical Planet 9, or interactions during the early, chaotic phase of solar system formation when the giant planets were migrating. The largest known Kuiper belt objects, Pluto, Eris, Makemake, and Haumea, all classified as dwarf planets, are substantial worlds in their own right, with diameters ranging from about 1,000 to 2,400 kilometers. But most Kuiper belt objects are much smaller, ranging from tens of kilometers to just a few hundred meters, too small to be observed directly. We infer their existence from statistical models and from the occasional close approach of a spacecraft. New Horizons, after its flyby of Pluto, continued deeper into the Kuiper belt, and in 2019 flew past a small object named Arakoth, previously designated 2014 MU69 and nicknamed Ultima Thule. Arakoth is tiny, only 36 kilometers long, but it is pristine, a contact binary, two lobes gently fused together in a low-velocity collision, with a smooth, lightly cratered surface and a color that is the reddest in the solar system, due to the accumulation of irradiated organic compounds. Arakoth is what planetesimals looked like in the earliest days of the solar system, and its gentle formation, no violent impacts, no heating, suggests that at least some regions of the protoplanetary disk were calm, allowing objects to grow by slow accretion rather than by catastrophic collisions. Studying Kuiper belt objects is difficult. They are far away, faint, and we have visited only 2 of them with spacecraft. But they hold clues to the formation and evolution of the solar system, and possibly to the conditions under which life could arise. Some Kuiper belt objects may have subsurface oceans, kept liquid by radioactive heating or by tidal interactions if they are part of binary systems. Future missions, perhaps a Kuiper belt orbiter or a fleet of small probes dispatched to multiple targets, could revolutionize our understanding of this distant, frozen frontier. 27. Oumuamua, the interstellar visitor. On October 19, 2017, a telescope in Hawaii detected a faint streak of light moving across the sky. This was not unusual. Asteroids and comets are discovered all the time. But when astronomers calculated the object's trajectory, they realized it was moving far too fast to be bound to the Sun's gravity. Its velocity was 26 kilometers per second relative to the Sun, and its path was hyperbolic, not elliptical. It had come from interstellar space, passed through the inner solar system, and was now racing back out toward the stars, never to return. This was the first confirmed interstellar object ever detected passing through our solar system, and it was given the name Oumuamua, a Hawaiian word meaning scout or messenger from afar. By the time astronomers realized what they were looking at, Oumuamua was already moving away, fading rapidly as it sped outward past Jupiter. Telescopes around the world turned toward it, capturing images and spectra before it became too faint to observe. What they found was deeply strange. Oumuamua was elongated, very elongated, shaped like a cigar or a needle, with a length roughly 10 times its width, about 400 meters long and 40 meters wide. No asteroid or comet in our solar system has such an extreme shape. Its surface was dark and red, similar to the color of Kuiper belt objects, suggesting it was covered with organic compounds irradiated by cosmic rays during its long journey through interstellar space. And, most puzzling of all, as Oumuamua moved away from the Sun, it accelerated slightly. Not much, but measurably, more than could be explained by the Sun's gravity alone. This acceleration is what sparked the most intense debate. When comets approach the Sun, they heat up, and volatile ices,
Water, carbon dioxide, methane, sublimate, jetting gas into space. The recoil from these jets acts like tiny rockets, pushing the comet and causing its orbit to deviate from a pure gravitational trajectory. This is called outgassing, and it is well documented for comets. The natural assumption was that Oumuamua was outgassing, despite showing no visible coma or tail, no cloud of gas and dust that normally surrounds an active comet. Perhaps the outgassing was too weak to be detected, or perhaps it was occurring in a way that didn't produce visible dust. But the amount of acceleration observed was difficult to reconcile with this explanation. Models showed that to produce the observed acceleration, Oumuamua would need to lose mass at a rate that, over the time it was observed, should have created a detectable coma. And yet, none was seen. So what was causing the acceleration? One hypothesis, proposed by Harvard astronomer Avi Loeb, is that Oumuamua is not a natural object, but an artificial one, specifically a light sail, a thin sheet of material pushed by radiation pressure from the sun. Radiation pressure is a real phenomenon. Photons from the sun carry momentum, and when they strike an object, they exert a tiny force. For ordinary asteroids, this force is negligible compared to gravity. But for a very thin, lightweight object, a sail essentially, radiation pressure can be significant, even dominant. If Oumuamua is a sail, its elongated shape would be explained. We are seeing the sail edge on, and its acceleration would be a natural consequence of sunlight pushing on it. This hypothesis is controversial, to say the least. Most scientists favor naturalistic explanations. One possibility is that Oumuamua is composed of a material that sublimates at lower temperatures than water ice, such as solid nitrogen or solid hydrogen, which would outgas even at the distances where Oumuamua was observed, and which would produce gas without much dust, making the outgassing difficult to detect. Another possibility is that Oumuamua is a fragment of a planet from another star system, broken apart by a collision or tidal disruption, and that its unusual shape is simply a result of being a shard rather than an intact body. Or perhaps Oumuamua's acceleration is due to asymmetric outgassing, gas jets from specific locations on the surface that happen to be oriented in such a way that they produce a net thrust without creating a visible coma in the direction we were observing from. We will never know for certain, because Oumuamua is gone, too far and too faint to observe any longer. It is now beyond the orbit of Neptune, heading out into the Oort cloud, and eventually into interstellar space, carrying with it the answers to the questions it raised. But the discovery of Oumuamua has proven something important. Interstellar objects do pass through our solar system, and they can be detected if we are looking. Since Oumuamua, a second interstellar object has been discovered, 2I Borisov, an interstellar comet detected in 2019 that, unlike Oumuamua, behaved like a normal comet with a visible coma and tail and no anomalous acceleration. This suggests that most interstellar objects are probably ordinary chunks of ice and rock, ejected from other planetary systems during their formation, or scattered out by gravitational interactions with giant planets. Oumuamua may be unusual even among interstellar objects, or it may be representative of a class of objects we have not yet recognized. Future surveys, like the Vera C. Rubin Observatory, currently under construction in Chile, will detect many more interstellar visitors, and perhaps among them, we will find others as strange as Oumuamua, and we will have the opportunity to study them more thoroughly, perhaps even to send a spacecraft to intercept one
before it leaves.
28. The mysterious planet 9. There may be another planet in our solar system, lurking in the darkness beyond Neptune, unseen and undiscovered. Not a dwarf planet like Pluto or Eris, but a true planet. A world 5 to 10 times the mass of Earth, orbiting the Sun at a distance so vast that it takes 10,000 to 20,000 years to complete a single orbit. This is Planet 9, a hypothetical object proposed in 2016 by astronomers Konstantin Batygin and Michael Brown of Caltech, based not on direct observation, but on the mathematics of gravity. The evidence for Planet 9 comes from the orbits of distant objects in the outer solar system, trans-Neptunian objects, with orbits that extend hundreds of astronomical units from the Sun. These objects, about a dozen of them with well-determined orbits, show a clustering in their orbital parameters that is statistically unlikely to be random. Their orbits are all tilted in the same direction. Their perihelia, the points where they come closest to the Sun, are clustered in the same region of space, and many of them have orbital planes that are tilted with respect to the plane of the solar system. Individually, these features could be coincidences, but together they point to a common cause: the gravitational influence of a massive, distant object shepherding the orbits of these smaller bodies into alignment. Computer simulations by Batygin, Brown, and other researchers have shown that if you place a planet of about 5 Earth masses at a distance of approximately 400 to 800 astronomical units from the Sun, with an orbital period of about 15,000 years, and run the simulation forward for billions of years, the orbits of trans-Neptunian objects evolve into configurations that match what we observe. The planet's gravity perturbs the objects, nudging them into resonances, tilting their orbits, and clustering their perihelia. The effect is subtle. Planet 9, if it exists, is far away and exerts only a weak gravitational pull on these distant objects, but over millions of years, the cumulative effect is significant. The simulations also predict other features of the outer solar system that we have observed but not fully explained. Objects with extreme orbital tilts, nearly perpendicular to the plane of the solar system, and objects in high-inclination retrograde orbits, moving in the opposite direction from the planets. These are difficult to explain by the known planets alone, but a distant Planet 9 could cause them. The evidence is circumstantial but compelling, and it has motivated astronomers to search for Planet 9 directly. But finding Planet 9 is extraordinarily difficult. If it is as far away as predicted, it would be incredibly faint, reflecting so little sunlight that it would be detectable only by the largest telescopes conducting deep surveys of the sky. And the search area is enormous. The predicted orbit is so large and so uncertain that Planet 9 could be almost anywhere in a huge swath of sky, and because it moves so slowly, taking thousands of years to orbit, its position changes only slightly from year to year, making it difficult to distinguish from background stars. Multiple searches have been conducted using telescopes like the Subaru telescope in Hawaii, the Dark Energy Survey in Chile, and data from the WISE infrared space telescope. But so far, nothing has been found. This does not mean Planet 9 doesn't exist. It may simply be fainter than expected, or it may be in a region of sky that has not yet been surveyed to sufficient depth, or it may be near its aphelion, the farthest point in its orbit, where it would be darkest and slowest. Some researchers have proposed alternative explanations for the clustering of trans-Neptunian orbits that do not require Planet 9. Perhaps the clustering is a selection bias, an artifact of where and how we have searched for these objects. Or perhaps it is caused by the collective gravitational influence of many smaller objects in the outer solar system, a disk of mass rather than a single planet. These alternatives are being debated, and distinguishing between them requires more data, more trans-Neptunian objects discovered, and their orbits measured precisely. The origin of Planet 9, if it exists, is also a mystery. One possibility is that it formed in the inner solar system, along with the other giant planets, and was later ejected to a distant orbit by gravitational interactions with Jupiter or Saturn. Simulations of planetary system evolution show that such ejections are common. Many planetary systems, perhaps most, lose one or more planets during their early chaotic phase, flinging them into distant orbits or out of the system entirely. Earth and the other terrestrial planets may owe their existence to such an ejection. If a fifth giant planet had remained in the inner solar system, its gravity would have disrupted the formation of the rocky planets. Another possibility is that Planet 9 is not native to our solar system at all, but was captured from another star. In the Sun's birth cluster, the dense group of stars where the Sun formed 4.5 billion years ago, stars were much closer together than they are now, and gravitational interactions between stars could have transferred planets from one system to another. A planet loosely bound to a neighboring star could have been pulled away by the Sun's gravity and captured into a distant orbit. This would explain why Planet 9's orbit is so different from the other planets, highly elongated and tilted, because it did not form from the Sun's protoplanetary disk. If Planet 9 is a captured planet, it would be a profound discovery, evidence of a violent and dynamic early history for our solar system. The search continues. The Vera C. Rubin Observatory, which will begin operations soon, will survey the entire visible sky repeatedly, detecting faint moving objects and potentially finding Planet 9 if it is within reach. And if Planet 9 is found, it will be one of the most significant discoveries in planetary science in decades. A new planet in our solar system, hiding in plain sight, waiting to be revealed. 29. The Oort cloud, the phantom frontier. At the very edge of the solar system, far beyond the orbits of the planets, beyond the Kuiper belt, beyond even the scattered disk and the detached objects, lies a region so distant and so diffuse that it has never been directly observed. This is the Oort cloud, a hypothetical sphere of icy bodies surrounding the Sun at distances ranging from 2,000 to 100,000 astronomical units, roughly halfway to the nearest star. If the solar system were the size of a coin, the Oort cloud would extend outward for tens of meters in all directions, a vast halo of frozen debris, invisible and unreachable by any telescope yet built. We infer its existence from the comets that occasionally fall inward from these distant reaches, plunging toward the Sun on orbits that take millions of years to complete. These are the long-period comets, comets like Hale-Bopp, Hyakutake, and Neowise, which appear suddenly in the inner solar system, brighten as they approach the Sun, and then fade as they swing back out toward the darkness, often never to return. Their orbits are nearly parabolic, meaning they are barely bound to the Sun, and they come from all directions, not confined to the plane of the solar system like the short-period comets from the Kuiper belt, but from the entire celestial sphere, as if they are raining down from a spherical cloud surrounding us. The Oort cloud was first proposed in 1950 by Dutch astronomer Jan Oort, who noticed that long-period comets seemed to originate from a preferred distance of about 50,000 astronomical units, and who suggested that there must be a reservoir of comets at that distance, weakly bound to the Sun and occasionally perturbed into the inner solar system by gravitational interactions with passing stars or by the tidal forces of the Milky Way galaxy itself. Oort's insight was based on statistics, the distribution of comet orbits, and it has been refined over the decades as we have discovered more comets and as computer simulations have allowed us to model the dynamics of the outer solar system in detail. The current picture is that the Oort cloud contains trillions of comets, perhaps as many as several trillion, with a total mass estimated at a few Earth masses. These comets are the remnants of the protoplanetary disk, icy planetesimals that formed in the region of the giant planets but were ejected to distant orbits by gravitational encounters with Jupiter, Saturn, Uranus, and Neptune during the turbulent early history of the solar system. Instead of being flung out of the solar system entirely, they were scattered just far enough that the Sun's gravity could still hold them, and over billions of years, their orbits were circularized and randomized by the gravitational influence of the Milky Way and by passing stars, forming the spherical cloud we infer today. The Oort cloud is divided into two regions. The inner Oort cloud, also called the Hills cloud, extends from about 2,000 to 20,000 astronomical units and is likely more disk-shaped, retaining some memory of the plane of the solar system. The outer Oort cloud extends from 20,000 to 100,000 astronomical units and is spherical. Objects in the outer Oort cloud are so weakly bound to the Sun that even a distant encounter with another star can change their orbit significantly, nudging some of them inward where they become visible as comets. And encounters with stars are not rare. The Sun moves through the galaxy, and over the lifetime of the solar system, it has passed through different regions with different stellar densities. Occasionally, a star comes close enough, within 1 or 2 light years, that its gravity perturbs the Oort cloud, sending a shower of comets toward the inner solar system. Evidence for such comet showers may exist in the geological record on Earth. Periods of increased impact cratering, such as the impact that created the Chicxulub crater and contributed to the extinction of the dinosaurs 66 million years ago, may coincide with passages of the Sun through regions of higher stellar density, or with close encounters with specific stars. But the Oort cloud is more than just a comet reservoir. It is a boundary, the farthest reach of the Sun's gravitational dominance. Beyond about 100,000 astronomical units, the Sun's gravity is so weak that objects are more influenced by the gravitational tide of the Milky Way galaxy than by the Sun. This is where the solar system ends and interstellar space truly begins. No spacecraft has reached the Oort cloud, and none will for tens of thousands of years. Voyager 1 and Voyager 2, the most distant human-made objects, are currently about 160 and 130 astronomical units from the Sun, respectively, traveling at about 3.5 astronomical units per year. At that speed, it will take them about 300 years to reach the inner edge of the Oort cloud, and roughly 30,000 years to pass through it and emerge on the other side. By that time, the spacecraft will be long dead, their power sources depleted, their instruments silent, drifting as inert chunks of metal and plastic through the void. But they will carry with them the golden records, messages from humanity encoded on phonograph discs, containing sounds and images of Earth, greetings in multiple languages, and music from cultures around the world. If the Oort cloud is inhabited, not by life, but by countless frozen comets, the voyagers will pass among them, unseen and unnoticed, silent ambassadors from a distant planet, journeying into the eternal night. 30. Black holes and the information paradox. Black holes are the universe's ultimate paradox. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are predicted by Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of space-time caused by mass and energy. When a massive star exhausts its nuclear fuel and collapses under its own gravity, it can compress its core to such extreme densities that it warps space-time into a singularity, a point of infinite density surrounded by an event horizon, the boundary beyond which escape is impossible. Once something crosses the event horizon, it is gone from the universe, fallen into the black hole, and no information about it can ever return. Or so we thought. In the 1970s, physicist Stephen Hawking discovered something that upended this picture. Using the principles of quantum mechanics, he showed that black holes are not completely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Virtual particle-antiparticle pairs, which constantly pop into existence and annihilate in empty space, can be separated by the intense tidal forces near a black hole's horizon, with one particle falling in and the other escaping as radiation. Over immense timescales, trillions upon trillions of years for stellar mass black holes, this radiation causes the black hole to lose mass and eventually evaporate completely. This discovery led to a profound problem known as the black hole information paradox. In quantum mechanics, information is never destroyed. It can be scrambled, encrypted, dispersed, but the total information content of a closed system remains constant. This is the principle of unitarity, and it underpins the predictability and reversibility of quantum mechanics. But if a black hole evaporates via Hawking radiation and the radiation is purely thermal, carrying no information about what fell into the black hole, then the information about all the matter that formed the black hole and everything that ever fell into it is lost when the black hole disappears. This violates unitarity. It creates a contradiction between general relativity, which allows information to be destroyed inside black holes, and quantum mechanics, which forbids it. For decades, physicists debated this paradox. Stephen Hawking initially argued that information is indeed destroyed, that black holes represent a breakdown of quantum mechanics. Others, including Leonard Susskind and Gerard Tufte, argued that information must be preserved, that Hawking radiation must somehow encode the information of everything that fell in, even if we cannot see how. The debate intensified in the 1990s with the development of the holographic principle and the discovery of ADS-CFT correspondence, a mathematical duality that relates certain gravitational theories to quantum field theories without gravity. These frameworks suggested that information is not lost, but is encoded on the event horizon itself, like a hologram, and is gradually released in the Hawking radiation in a highly scrambled form. In 2004, Hawking conceded that he had been wrong and that information is preserved, though the mechanism remains unclear. Recent work has focused on the island formula and the role of quantum entanglement between the interior and exterior of a black hole, suggesting that information begins to leak out in the Hawking radiation once the black hole has evaporated to about half its original mass. But the paradox is not fully resolved. We do not have a complete theory of quantum gravity, a theory that unifies general relativity and quantum mechanics. And without such a theory, we cannot describe what happens at the singularity or precisely how information escapes from a black hole. The information paradox remains one of the deepest puzzles in theoretical physics, a window into the incompleteness of our current understanding, and solving it may require a revolutionary new framework that transcends both relativity and quantum mechanics.